Have you ever looked up at the night sky and felt a profound sense of wonder? That deep, quiet awe that washes over you as you stare into an infinite ocean of possibilities? We trace the familiar patterns of constellations drawn by our ancestors. We follow the steady, reassuring glow of the planets on their celestial track, and we make a wish on the fleeting, fiery streak of a meteor. It is a cosmic ballet we have come to know and love, predictable, majestic, and beautiful. But what if, one night, something appeared that refused to follow the rules? What if a traveler from a distant, unknown shore washed up on our cosmic beach? A visitor so strange, so out of place, that it defied our every expectation and challenged the very foundations of what we thought we knew about the universe. This is not a work of fiction. This is the story of 3I Atlas, an object that screamed into our solar system from the unimaginable blackness between the stars. In doing so, it has forced us to confront a question as thrilling as it is unsettling. Are we looking at the strangest comet ever discovered? Or are we witnessing the arrival of something else entirely? Imagine the scene. It's September 2024. In the crisp, clear air of a Hawaiian mountaintop, the robotic eyes of the Atlas Survey telescopes sweep across the heavens. Their vigil is tireless, their mission critical: to catalog the near-Earth asteroids that could, one day, pose a threat to our world. It is a routine, methodical task, a nightly digital search for tiny blips of light moving against the static backdrop of the stars. But then, a new blip appears on their sensors. It's faint. It's moving impossibly fast. At first, it's just another data point, another celestial wanderer logged in an endless archive. But as astronomers around the globe begin to track its path, a collective sense of astonishment begins to ripple through the community. This is no ordinary object. The calculations are checked and then checked again. The numbers are stark, beautiful, and unequivocal. This visitor, now officially designated 3I Atlas, did not originate from the cold, dark fringes of our own solar system, not from the Kuiper Belt or the distant Oort cloud where our own comets are born. Its velocity is simply too high, its trajectory too extreme. It is an interstellar object, a true alien to our system, and only the third one ever confirmed in all of human history. You've probably heard the headlines, haven't you? Whispers of an interstellar comet, talk of strange chemistry, and reports of a bold Harvard astronomer making claims that seem to verge on the unbelievable. But here is what they are not telling you, the chilling detail that sends a shiver down the spine of even the most sober-minded scientist. In less than 1 month from now, in late October 2025, 3I Atlas will perform a cosmic vanishing act. For 4 long weeks, it will disappear behind the sun in an event called a solar conjunction, a total observational blackout. Every telescope on Earth, from the giants peering from remote mountaintops to the magnificent Hubble Space Telescope orbiting above us, will be rendered useless, completely blinded by the incandescent glare of our own star. And it is during this window of darkness, this period of enforced ignorance, that the true test will come. If the audacious theories of Professor Ave Loeb are correct, if this object is more than just a primordial lump of ice and rock, this is when it could make its move. It could maneuver. It could change its course. It could deploy secondary objects. And we would have absolutely no way of catching it in the act. Let's just pause for a moment and really absorb the implications of that. We are on the cusp of witnessing the most active and scientifically crucial phase of this object-'s journey through our cosmic neighborhood. And right at that precise moment, our vision will be completely cut off. Is this a staggering coincidence? A case of cosmic bad luck? Or is it something more? Is it convenient? This is the central question that hangs over the entire story of 3I Atlas, a puzzle that begins not with its chemistry, but with its path across the sky. Picture our solar system as a vast, flat vinyl record. The sun is the spindle at the center, and the planet's Earth included orbit in concentric grooves on this flat disk, a plane we call the ecliptic. It is, for all intents and purposes, our solar system's main highway. Most interstellar visitors, the comets and asteroids flung from other star systems by gravitational chaos, are like cosmic daredevils. They tumble into our system from random, chaotic directions, streaking across the lanes at wild, bizarre angles. They don't use the highway, but 3I Atlas does. It is staying in its lane. Its path is almost perfectly flat against the ecliptic, off by a mere 5 degrees. In a universe of infinite, random angles, that is an unnervingly precise piece of cosmic driving. It is like standing on a street corner and seeing a car from another country turn onto your road, perfectly obeying the local traffic laws. As Professor Loeb himself put it, with his characteristic refusal to mince words, this looks more like a flight plan than a random plunge, and the strangeness is just getting started. The chemistry of this object is, frankly, bizarre. When our most powerful instruments, including the incredible James Webb Space Telescope, analyzed the cloud of gas and dust surrounding 3I Atlas, they found something that turned our established models of comets completely on their head. The measured ratio of carbon dioxide to water is an astonishing 8-to-1. Let me put that into perspective for you. Comets are famously and accurately described as dirty snowballs. The snow is water ice. Water is supposed to be the main ingredient, the dominant substance that sublimates and erupts into a brilliant coma and tail as the comet nears the sun. But here, water is just a minor component. This object is venting 8 times more carbon dioxide than water. Just imagine a snowman made almost entirely of dry ice. It can exist, but it's certainly not what you'd expect to find. Then there is the nickel. Our telescopes detected a cloud of nickel atoms being vented from the object. This isn't unheard of, but what is truly baffling is that there is virtually no corresponding iron. In the cosmos, iron and nickel are like inseparable chemical twins, forged together in the violet hearts of dying stars. In any natural rock or metallic body, you simply do not find one without the other. Yet, 3I Atlas is showing us strong signals of nickel, while the iron remains mysteriously absent. Our best models of cometary physics struggle to explain this. We are forced to invoke exotic, unproven chemical pathways to even begin to make sense of it. And the object's path, this supposed flight plan, seems to thread its way past key points of interest in our solar system like a tourist on a grand pre-planned tour. On October 3rd, 2025, just days from now, it makes a relatively close pass of Mars. Then, it swings by the Sun at the end of October, right when it enters that observational blackout. And after it re-emerges from the Sun's glare, its trajectory takes it for a close encounter with Jupiter, the king of our solar system. In March of 2026, Mars, Sun, Jupiter. To a mission planner, those look like waypoints. Could this all be a series of incredible, random alignments? Of course. Coincidences happen every day. The universe is not required to make sense to our pattern-seeking human brains. But as the anomalies continue to pile up the trajectory, the chemistry, the timing, the argument from mere coincidence begins to feel strained. Let me offer you a thought experiment. Imagine you're standing in the middle of a vast, open field. A mile away, a person you can't see throws a dart. That single dart soars through the air and lands just inches from your feet. Would your first assumption be that it was a random, lucky throw? Or would you be entirely justified in at least asking the question, were they aiming at me? 3I Atlas is that dart. And we are the ones standing in the field, starting to wonder who or what threw it. But here's what Professor Loeb is really saying, and it's a point that is perhaps more profound and unsettling than the possibility of alien probes. This story is not just about a weird rock in space. This is a story about us. It is about whether we, as a species, are capable of investigating anomalies seriously. It's about our ability to sit with profound uncertainty, to hold two competing ideas in our minds at once, natural and the artificial, without immediately collapsing into knee-jerk dismissal on one side or baseless hysteria on the other. And right now, as a scientific community and as a global society, we are struggling with that test. We find ourselves caught between the tantalizing desire to believe and the ingrained scientific imperative to doubt. Over the course of this journey, we are going to perform a deep dive into this cosmic mystery. We have spent countless hours analyzing every observation, every spectrum, every trajectory model available. We are going to show you with the actual data exactly what makes 3I Atlas genuinely different from any comet we have ever seen. We will explore what the solar conjunction, this impending blackout, actually means from both a tactical and a scientific standpoint. And we will explain why the next 4 weeks could matter more than you can possibly imagine. Because whether this object is the weirdest comet in history, a pristine messenger from the dawn of another star system, carrying secrets we can't yet comprehend, or something else entirely, how we respond to it right now is the real test. Are we demonstrating a readiness for the unknown? Or are we just exposing how fundamentally unprepared we are for a universe that might be far stranger and far more populated than we have ever dared to imagine? So get comfortable, settle in. The journey into the heart of this mystery begins now. We will dissect the evidence, piece by piece, starting with that unnervingly precise trajectory. We will look at the hard data, the formal numbers that prove this object is not from around here. We will explore its incredible speed, its backward, retrograde path, and why that simple 5-degree inclination from our solar system's highway keeps astronomers up at night. This is the story of 3I Atlas, and it is a story that is still being written, with the most important chapter about to unfold in the darkness, behind the blinding light of our sun. Let's get into it. So, how does a simple line drawn across a star chart become the first chapter in a cosmic detective story? How can a trajectory, a mere path through the void, cause so many seasoned scientists to lean forward with a mixture of excitement and unease? The answer lies in one of the most fundamental principles of our solar system, its structure. To understand just how profoundly strange the journey of 3I Atlas is, we first have to appreciate the beautiful, orderly architecture of our own cosmic home. Just imagine, for a moment, that you could float high above our solar system and look down upon it. What you would see is not a random scattering of worlds, but a magnificent, dynamic system organized with the elegance of a spinning disk. At the heart of it all, blazing with incomprehensible power, is our sun. And orbiting that sun, in an almost perfectly flat plane, are the 8 planets. From Mercury out to Neptune, they all travel in the same direction, following the same set of unwritten rules, like celestial skaters circling on a vast, frozen pond. This flat, shared orbital space is what astronomers call the ecliptic plane. It is not just a scientific term. It is the very foundation of our solar system's stability and history. It is the grand cosmic highway upon which all the worlds we know travel. Now, for billions of years, our solar system has played host to visitors from the interstellar deep. These are the orphans of the galaxy, rogue comets and asteroids, cast out from their own nascent star systems by the chaotic gravitational dance of their formation. They have wandered the desolate wilderness between the stars for millions, perhaps billions of years. Their journeys are random, their paths scarred by the gravitational nudges of countless passing stars. When they finally stumble into our solar system, they arrive like leaves scattered in a hurricane. They plunge in from above, they sweep up from below, their paths tilted at wild, unpredictable angles to our neat, orderly ecliptic highway. They are the interlopers, the outsiders, and their chaotic trajectories are a clear sign that they are not from around here. That is what we have always seen. That is what we have always expected. Until now, 3I Atlas is different. It is not tumbling chaotically into our system. It is gliding. When the hard-working astronomers at the Atlas Survey in Hawaii first spotted that faint speck of light in September 2024, they initiated a global chain of observation. The Minor Planet Center, the world's clearinghouse for all things that move in the night sky, issued an alert. Instantly, telescopes around the planet Pan-STARRS, the Canada-France-Hawaii Telescope, and dozens of other professional facilities swiveled their great eyes to this new arrival. They all confirmed the same baffling thing. 3. I-Atlas was an interstellar object, no doubt about it. But it was an interstellar object that was behaving with an almost eerie sense of decorum. It was staying in its lane. The formal numbers tell the story with a chilling precision. The object has an orbital inclination of approximately 175.11 degrees. In astronomical terms, this means it is traveling retrograde. It is moving backward relative to the planets, like a car driving the wrong way down the highway. While unusual, this isn't the truly shocking part. The key, the detail that makes astronomers pause and reread their printouts, is that its path is only about 5 degrees off the flat ecliptic plane. Let's try to grasp the sheer improbability of that. Imagine the sky is a giant sphere, a celestial globe surrounding us. An object arriving from a random point on that sphere has a 360-degree range of possible angles. For it to arrive within that tiny 5-degree slice of our solar system's highway is statistically remarkable. It's like throwing a paper airplane off the top of the Empire State Building and having it glide perfectly parallel to the pavement for miles. Professor Avi Loeb, the Harvard astronomer who has become the most vocal proponent of investigating this object's strangeness, didn't hold back. He stated bluntly that this looks far more like a flight plan than a random cosmic plunge. The phrase hangs in the air, loaded with implication. A plan implies intent. It implies a planner. But the trajectory isn't just about the angle of approach. It's also about the sheer, mind-bending velocity. This is where we move from a statistical improbability to an absolute certainty. This object is not one of ours. In orbital mechanics, we have a value called eccentricity, which, in simple terms, describes how stretched out an orbit is. A perfect circle has an eccentricity of 0. The elongated, oval-shaped orbits of comets in our own solar system might have eccentricities approaching 1.0. An eccentricity of exactly 1.0 means the object is on a parabolic escape trajectory. It has just enough energy to escape the sun's gravity and never return. Anything above 1.0 is called a hyperbolic trajectory. It means the object came screaming in from interstellar space with so much excess energy that the sun's gravity is little more than a temporary inconvenience. It will swing around our star and be flung back out into the void, destined to wander for eternity. The eccentricity of 3 I-Atlas is approximately 6. That is not a typo. It is a number of such violence and power that it almost beggars belief. It is the orbital equivalent of a Formula One car entering a quiet suburban cul-de-sac at Mach 3. It didn't just drift into our solar system. It burst onto the scene like a cannonball. This incredible speed is the ironclad, indisputable proof that it was born in another star system. There is simply no way an object from within our own solar system could ever achieve such a velocity. Its alien origin is a scientific fact, confirmed by observatories across the globe. This is real. This is here. And it is heading for the sun. Its point of closest approach to our star, a moment known as perihelion, will occur between October 29th and 30th, 2025. At that moment, it will be approximately 0.96 astronomical units from the sun. That is, just inside the orbit of Earth, where it will be subjected to the most intense blast of solar radiation. While it will be relatively close to us in cosmic terms, NASA and the European Space Agency have been crystal clear. There is absolutely no threat to Earth. Its closest approach to our planet will be a comfortable 1.8 astronomical units, or about 168 million miles. The geometry simply does not allow for an impact. But it is precisely this geometry that gets so interesting for other reasons. Because the path of 3I Atlas doesn't just bring it close to the Sun. It seems to create a sequence of remarkable opportunities, a grand tour of the inner solar system. Let's trace the itinerary. First stop, Mars. On October 3, 2025, just days from now, the object will pass relatively close to the red planet. This is such a significant event that the European Space Agency is already planning to redirect its assets currently orbiting Mars, the Mars Express Orbiter and the Trace Gas Orbiter, to aim their instruments at this fleeting visitor. Second stop, the Sun. In late October, it reaches perihelion, its moment of peak activity, where it will be heated most intensely. And it is here, at this most scientifically crucial moment, that it will slip behind the Sun from our perspective, entering the 4-week observational blackout we spoke of earlier. Third stop, Jupiter. After it reemerges from the Sun's glare, its journey is not over. On March 16, 2026, it will make a pass within 0.358 astronomical units, a mere 33 million miles of Jupiter, the colossal king of our solar system. Mars, Sun, Jupiter, 3 distinct vantage points, 3 unique environments. Each stop offers a different potential sensing opportunity if, for instance, you were a probe designed to conduct a comprehensive survey of a new and interesting star system. And sandwich it right in the middle of this incredible sequence is the solar conjunction, that period where it passes behind the Sun, and we on Earth are rendered temporarily blind. If you were deliberately planning a course through the inner solar system, and you wanted a built-in window of time where Earth's prying eyes would be unable to watch you, you would be hard-pressed to design a better, more convenient scenario. Now, let's be scientifically honest and rigorous here. We must be cautious. A low inclination, a flat trajectory, does not automatically scream alien technology. There are potential natural explanations, though they themselves rely on a degree of cosmic coincidence. Perhaps 3I Atlas was ejected from a planetary system that, by pure chance, happens to be aligned on the same plane as ours. Or perhaps its trajectory was bent and twisted into alignment by a close encounter with another star during its long journey through the galaxy. These scenarios are plausible, but they require a certain amount of luck. We also have to consider what is known as selection bias. Our survey telescopes are aimed primarily along the ecliptic plane, because that is where the most interesting objects in our solar system reside. It is therefore possible that we are simply better at detecting interstellar objects that happen to travel along that plane. But here is the fact that keeps astronomers coming back to the drawing board, the detail that keeps the conversation going late into the night. In the entire history of astronomy, we have only ever detected 3 confirmed interstellar objects. 3. The first was 1I Oumuamua in 2017. It arrived on a steeply tilted orbit, was strangely elongated, and exhibited a mysterious acceleration that defied any easy explanation. It was profoundly weird. The second was 2I Borisov in 2019. It was a welcome relief to many astronomers because it looked and behaved almost exactly like a normal comet from our own solar system, just visiting from far away. It was reassuringly normal. And now we have 3I Atlas, our third visitor, arriving on this peculiarly flat trajectory, timing its closest and most active approach to the Sun to coincide perfectly with a period when we are unable to watch. Out of a tiny sample size of 3, 2 of them are deeply, fundamentally strange. That is not a robust statistical sample, but it is a curiosity so profound that it demands our full attention. As Professor Loeb describes it, 3I Atlas is following a rail-flat glide path followed by a sun eclipse. From a purely tactical standpoint, if someone or something wanted to approach the inner solar system while minimizing our ability to observe them at the most critical moment. This would be an almost optimal solution. We human beings are creatures of pattern recognition. It is a skill that is hardwired into our brains, a survival instinct that kept our ancestors alive by allowing them to see the tiger hiding in the tall grass. But it also means we must be cautious of seeing agency where there is only randomness, of seeing faces in the clouds. Coincidences do happen. The universe is under no obligation to be simple. Yet, consider that thought experiment one more time. You are in a field. A dart, thrown from a mile away, lands at your feet. Now, what if you learned that out of the last 3 darts thrown, 2 of them had landed within inches of you? At what point do you stop calling it a coincidence and start wondering if you are being targeted? The trajectory of 3I Atlas is the first great mystery, the first clue that suggests we may be dealing with something truly unprecedented. But its path is only the beginning of the story. To truly understand how strange this visitor is, we must now look beyond its orbit and peer into its very soul, its chemistry, and its behavior under the fierce heat of our sun. Because when our best instruments were aimed at this visitor, what they saw was even stranger than its path. Some comets glow. This one might have headlights. A path through space, no matter how strange, is still just a line on a map. It's the ghost of a journey, a trace of where an object has been and where it is going. But it tells you nothing about the object itself. What is this traveler made of? What is its nature? Is it a chaotic, tumbling mountain of primordial ice, or is it something more structured, more coherent? To answer that, we must move beyond tracking its trajectory, and instead turn our most powerful eyes directly upon it. We must stare into its heart and decode the light it sends back to us across the void. And when we did just that, the mystery of 3I Atlas deepened, for the light it returned was unlike anything we had expected. It was the light of a ghost in a machine. Our story now takes us to July 21st, 2025. High above the Earth, far from the distorting haze of our atmosphere, the magnificent Hubble Space Telescope executes a silent, graceful pivot. Its target, the faint, fast-moving smudge of 3I Atlas. For years, Hubble has been our window to the cosmos, capturing images of such breathtaking beauty and clarity that they have become modern icons of science and art. Now, it was being tasked with taking the clearest portrait we had of our interstellar visitor. And what Hubble revealed was, at first, both familiar and deeply reassuring. The good news was, it looked like a comet, few. There, in the crisp, detailed image, was a distinct central point of light, the nucleus, the solid core of the object. Its size was difficult to pin down precisely, because it was shrouded in a fuzzy cloud of its own making. But astronomers estimated it to be somewhere between 320 meters and 5.6 kilometers across. That is a very wide range, but the important takeaway is this. It is small enough to be a perfectly natural object, yet large enough to be structurally significant. It wasn't a tiny pebble, nor was it an impossibly large megastructure. It was in the cometary sweet spot. Hubble also captured the classic, iconic signatures of a comet feeling the heat of a star. There was a beautiful sunward dust plume, a fountain of material erupting from the side facing the sun, and trailing behind it was a faint but distinct anti-solar tail. It was a perfect textbook illustration of cometary activity. As 3I Atlas approached the sun, the solar radiation was baking its surface, causing volatile ices to sublimate, to turn directly from a solid into a gas. This outgassing was carrying dust and debris along with it, and the constant pressure of the solar wind was pushing that material away from the sun, creating the ghostly, beautiful tail we associate with comets. Later observations by the Gemini Observatory in Chile confirmed an even longer tail stretching behind the object. So by all initial appearances, this thing was acting its part. It was outgassing. It was behaving. It was, for all intents and purposes, a comet. But then Avi Loeb, looked at the very same data, the very same images, and he saw something else. This is where the story takes its first sharp turn into the truly strange. Loeb, with his eye for anomalies, described what he called a forward glow. He saw a luminous region on the sunward face of the object that was unusually bright and directional. To him, it did not quite match the standard, diffuse, symmetrical morphology of a typical comet's coma. Let's try to visualize the difference. Imagine a dusty chalkboard eraser. If you blow on it, you get a diffuse, shapeless cloud of chalk dust. That's a standard comet coma. But what Loeb saw was more like a flashlight beam shining through a fog grider, more focused, more directed toward the sun. He was careful to label this as his interpretation, not an established fact. But to him, this looked less like dust, passively scattering sunlight, and more like something was actively glowing toward the sun. Mainstream astronomers looked at the images and saw a dust plume, a perfectly natural jet of material. Loeb looked at the same image and saw headlights. Who was right? Well, that depends entirely on the data you choose to emphasize. The Hubble and Gemini observations absolutely show tailing activity. There is no dispute there. But Loeb's point is about the distribution of that brightness. In a typical comet, you expect a roughly symmetrical halo of light around the nucleus, sculpted by the solar wind. What he was noting was a stark asymmetry, a concentration of light on the sunward side that seemed excessive for dust alone. Now, there are potential natural explanations for this. The nucleus of a comet is a spinning, irregular body. It could have active dust jets that, due to its rotation, are preferentially pointing sunward at that particular moment. Or perhaps there are unique surface features, like cliffs or valleys, that are concentrating the outgassing in one specific direction. These are perfectly valid and plausible scientific hypotheses. Or, if you are Avi Loeb, you entertain a third, more exotic possibility. It could be active thermal management. It could be the signature of an object deliberately venting material to control its internal temperature as it makes its perilous approach to a star. Let us table that unsettling thought for just a moment and travel deeper into the invisible spectrum of light. Because to get to the next clue, we need an even more powerful tool, an instrument so revolutionary it is changing our view of the entire universe. We need the James Webb Space Telescope. On August 6, 2025, this golden-eyed marvel aimed its sensitive spectrometers at 3I Atlas. The James Webb doesn't care about visible light. It sees in the infrared the realm of heat and molecular vibrations. It is, in essence, a cosmic chemical sniffer, capable of telling us exactly what this object is made of and what gases it is venting into space. The results were released to the public on August 25th, and they sent an immediate shockwave of bafflement through the entire planetary science community. The culprit was carbon dioxide. Lots and lots of carbon dioxide. Specifically, the James Webb Space Telescope measured a ratio of carbon dioxide to water C, O2 to H2O of approximately 8:1. Let me be absolutely clear about why this number is so profoundly strange. Comets are, as we've said, dirty snowballs. The primary ingredient, the very substance that defines a comet, is supposed to be water ice. It is the water that sublimates, creating the vast coma and tail. Other gases like carbon dioxide are usually present, but as secondary components, trace contaminants mixed into the dominant water ice. A typical ratio might be 10 times more water than carbon dioxide. A comet with equal parts water and CO2 would be considered unusual, but a ratio of 8:1? This means that for every 1 molecule of water this object is releasing, it is venting 8 molecules of carbon dioxide. That is not just unusual. It is a number that firmly resides in the what the hell is going on category of cometary science. This isn't a dirty snowball. It's a dry ice mountain. And this wasn't a one-off fluke. An entirely different space telescope, An infrared surveyor called Spherix also observed 3I Atlas in late 2025. What it found was extraordinary. It detected an absolutely enormous carbon dioxide coma, a vast bubble of CO2 gas extending at least 348,000 kilometers from the nucleus. To give you a sense of scale, the distance from the Earth to the Moon is about 384,000 kilometers. This object is wrapped in a cloud of carbon dioxide that is nearly as wide as the Earth-Moon system. And here is the kicker. Spherix did not detect comparable amounts of water or carbon monoxide at that same time. The carbon dioxide dominance is not a quirk of a single measurement. It is a consistent, verified, and frankly bizarre feature of this object. So, why does this matter? Because it fundamentally challenges our understanding of how comets are formed. In the cold, dark nurseries of star systems, water ice is abundant and freezes out at relatively warm temperatures. Carbon dioxide needs slightly colder conditions to condense. A comet that is made of 8 parts CO2 to 1 part water must have formed in a very specific, very cold thermal environment, perhaps far out in its home system, near what is called the carbon dioxide ice line. Or perhaps its surface was heavily processed by cosmic radiation over millions of years in interstellar space, sealing off the water ice buried deep beneath a crust of carbon dioxide. These natural explanations are possible, but they require very specific and somewhat rare conditions. Or, if you're inclined toward more exotic explanations, you might note that carbon dioxide makes for an absolutely excellent working fluid. It sublimates at much lower temperatures than water, meaning it turns to gas more easily. It is a key component in many industrial and engineering processes. And if you were an engineer designing a passive cooling system for a spacecraft that needed to approach a star and shed a tremendous amount of heat, carbon dioxide would be right at the top of your short list of materials. A spacecraft venting CO2 as a coolant would, from a distance, look chemically a lot like what the James Webb Space Telescope and Spherix observed. But wait, the chemical weirdness is not over. We have one more piece of evidence to consider, and it may be the most difficult to explain of all. Enter nickel. Using the Powerhouse Very Large Telescope in Chile, astronomers analyzed the light from the coma with extreme precision. They detected the telltale emission lines from neutral nickel atoms glowing in the cloud of gas surrounding 3I Atlas. Now, finding nickel in a comet isn't unheard of, but it's usually faint, and it is associated with the vaporization of metal-bearing dust grains very close to the nucleus, where the solar heating is most intense. What is so strange here is the amount of nickel being detected, and the almost complete absence of its cosmic companion, iron. Iron and nickel are forged in the same stellar furnaces. In any natural, rocky, or metallic body in the universe, from asteroids to planets to meteorites, they are found together. They are cosmic twins, almost always appearing in predictable ratios. You simply do not see one without the other. Yet, that is precisely what we are seeing in 3I Atlas. Strong, clear spectral lines of nickel. Weak or entirely absent lines of iron. How on earth do you explain that? One possible natural mechanism involves something called organometallic compounds, exotic molecules where metal atoms are bonded to organic carbon chains. Nickel can form certain volatile compounds, like nickel tetracarbonyl, that could sublimate at relatively low temperatures and be broken apart by ultraviolet light, releasing the nickel atoms to glow in the sunlight. Iron can do similar chemistry, but the pathways are different, and it is theoretically possible that under certain specific conditions, you might release nickel preferentially over iron. It is an explanation that lives at the far edge of known chemistry. It is plausible, but it is not simple. Avi Loeb, writing in late September 2025, highlighted what he called the extreme nickel production and suggested that it could be an indicator of non-thermal or even engineered heating, a controlled release of specific materials, rather than the passive, chaotic sublimation of a natural comet. This, of course, is a hypothesis, not a fact. But it is a testable one. If, as 3I Atlas gets closer and hotter, iron emission lines finally start to appear in the expected ratio, that would strongly support the natural, exotic chemistry explanation. But if iron never shows up, or if the nickel-to-iron ratio remains bizarrely skewed, then that becomes a profound mystery that is incredibly difficult to explain with natural physics. So, let's take a step back and synthesize what we now have on the table. We have a visitor from interstellar space on a remarkably flat flight plan trajectory. It exhibits a potentially asymmetric forward glow that one prominent astronomer interprets as headlights. Its chemistry is dominated by an 8-to-1 ratio of carbon dioxide to water, among the highest ever measured. And it is venting strong signals of nickel without its inseparable cosmic twin, iron. None of these things, taken in isolation, is completely impossible to explain naturally. But when you stack them all together, the portrait that emerges is of an object that is not just an outlier, but an outlier among outliers. The competing models are now in sharp relief. Model 1 3I Atlas is a completely natural, if exceptionally weird, comet. It formed in a very specific and unusual environment in its home star system, giving it its strange chemistry. Its trajectory is a lucky coincidence. And its behavior, while puzzling, will ultimately be explained by known, if exotic, physics. Model 2 3I Atlas is something artificial. It is a technological object using the sun's thermal energy for power or propulsion. It is venting carbon dioxide as a coolant or working fluid, and it is outgassing nickel-bearing materials as an incidental byproduct of its internal operations. We do not have a consensus. We do not have a peer-reviewed explanation that comfortably ties all these anomalies together. What we have is a set of data that refuses to fit neatly into our existing boxes, and a ticking clock. The object is just weeks away from disappearing behind the sun. The question hanging in the air, thick with possibility, is: are we looking at the universe's weirdest comet, or are we looking at technology? And if it is technology, whose is it? This is where we need a system. When you are dealing with a mystery of this magnitude, you cannot rely on gut feelings or shouting opinions. You need a framework for quantifying just how weird something is, a way of keeping score. Because when you're dealing with potential visitors from other stars, you need a system for deciding when weird crosses the line into artificial. That system now exists. So let's talk about how you score a cosmic mystery. Imagine you are a detective standing at the threshold of a crime scene. The room is in disarray. Clues are scattered everywhere. A fingerprint on a glass, a strange fiber on the carpet, a window left inexplicably open. How do you begin to make sense of it all? You don't just jump to conclusions. You use a system. You methodically evaluate each piece of evidence, weighing its significance, considering its context, and scoring it against what you know about the world. You look for patterns, for connections, for anything that elevates a simple anomaly into a meaningful lid. In astronomy, when we are faced with an object that whispers of possibilities beyond our current understanding, we need a similar system. We need a way to move beyond the binary, often emotional debate of "it's just a rock" versus "it's aliens." We need a rational, evidence-based framework for evaluating the strangeness, for quantifying the anomalies, and for tracking our level of uncertainty. And in the wake of the bewildering passage of Oumuamua, Professor Avi Loeb proposed just such a system. He calls it the Interstellar Object Screening System, IOSS, but it has become more popularly known as the Loeb scale. Think of it as the Torino scale for asteroid impacts. But instead of measuring the risk of a collision with Earth, it measures the probability of artificiality. It is a simple, elegant, 0 to 10 classification scheme designed to rank interstellar objects based on how anomalous they are, and how well or how poorly natural explanations can account for their behavior. A score of 0 means the object is completely normal. a textbook case, definitively natural. A score of 10 means we have incontrovertible, smoking gun proof of technology, confirmed artificial, case closed. The real action, the thrilling scientific debate, happens in the murky middle of the scale. This is the realm of uncertainty, where strange features must be carefully weighed against plausible, if exotic, natural explanations. It's a dynamic system, not a final judgment. An object's score can, and should, change as new data comes in. It is a tool for organizing our uncertainty, not for declaring a verdict. So, let's use this scale to understand our cast of interstellar characters. At the very bottom, sitting comfortably near a zero, is 2I Borisov, the second interstellar visitor discovered in 2019. Borisov was a gift to astronomers because it was so wonderfully, beautifully normal. It looked like a comet. It behaved like a comet. It had a nice, predictable composition, rich in carbon monoxide, perfectly consistent with its formation in a cold, dark molecular cloud around another star. Borisov was exotic only because of its address. Its properties were thoroughly mundane. Score, natural, mystery solved, move along. At the other end of the spectrum, we have the high numbers, the 8s, 9s, and 10s. The Loeb scale reserves these top tiers for objects where we have strong, unambiguous, and reproducible evidence of technology. We are talking about the kind of evidence that would end the debate overnight. Things like the detection of narrowband radio transmissions carrying a complex, patterned signal, or direct high-resolution imaging that reveals geometric structures, flat surfaces, or modular components that simply cannot be explained by natural geology. Or perhaps the discovery of exotic, highly processed industrial alloys in its spectral signature. To be clear, we have never, in all of human history, found an object that scores an 8 or above. We haven't even come close. And then there is one Oumuamua. Oumuamua, the first interstellar visitor, discovered in 2017, and the object that continues to give astronomers headaches to this day. Oumuamua was bizarre from the moment it was detected. It was highly elongated, tumbling strangely through space. Crucially, it showed no visible coma or tail, no cloud of gas and dust, even as it passed incredibly close to the sun. And then came the knockout punch. It exhibited a tiny but clear non-gravitational acceleration. It was deviating from its predicted path, as if something was gently pushing it. Comets do this all the time. The outgassing of jets of gas and dust acts like a set of tiny, unpredictable rocket thrusters, pushing the comet around. But Oumuamua showed no signs of outgassing. No dust, no gas. Just a smooth, steady acceleration away from the sun. It was this anomaly that famously led Loeb to suggest that it could be a light sail of thin, reflective sheet pushed by the pressure of sunlight itself, either a piece of defunct alien technology or a derelict probe. The mainstream explanation eventually settled on the idea that it must have been outgassing something invisible, like pure hydrogen, which wouldn't produce a visible coma, but could still provide the necessary thrust. On his own scale, Loeb scores Oumuamua at around a 7. Highly anomalous, not easily explained by any single natural phenomenon, but falling just short of confirmed artificial. The wider scientific community would likely score it much lower, perhaps a 3 or a 4 unusual, deserving of intense study, but probably a natural object with some exotic new physics we have yet to fully understand. So, with that context, where does our current visitor, 3I Atlas, fall on this scale? Loeb himself describes it as being in the high middle, not quite as extreme and unexplainable as Oumuamua, but significantly weirder than the reassuringly normal Borisov. Let's break it down and score it, feature by feature, like a detective examining the evidence. Geometry, the low inclination, that flight plan trajectory, just 5 degrees off the ecliptic, is statistically uncommon for a random interstellar arrival. It's not impossible, but it is an eyebrow-raising coincidence. That ticks the score up. Timing, the fact that its perihelion passage, its moment of peak activity, coincides perfectly with the solar conjunction. That 4-week blind spot for Earth-based observers is another remarkable coincidence. Is it just bad luck? Or is it, as we've asked before, convenient? Another tick up. Chemistry. The extreme carbon dioxide to water ratio of 8:1 is on the far, far edge of known cometary diversity. The enormous CO2 coma detected by Sphyrix adds significant weight to this anomaly. It points to a very specific and unusual formation history, or something else. This is a significant tick up. The nickel anomaly. The strong nickel emission without corresponding iron is incredibly difficult to explain with standard cometary models. The organometallic pathways are a potential natural explanation, but they are themselves exotic and unproven. If iron fails to appear as the object heats up, this anomaly becomes deeply puzzling. This ticks the score up even further. Optical asymmetries. Loeb's interpretation of a forward glow, or headlights, is currently contested and remains his personal interpretation. But if it were to be confirmed by independent analysis, it would suggest a directed, active emission rather than passive, scattered sunlight. That would be a very big deal. For now, we hold this as a potential, but unconfirmed, point of interest. So where does that leave us? Right now, the score for 3I Atlas sits somewhere around a 5 or a 6. It is deeply interesting. It is profoundly weird. It is absolutely worthy of our full attention. But it is not yet conclusive. The natural comet hypothesis, while strained and requiring a great deal of special pleading, has not yet been broken. But here is the crucial thing to remember about the Loeb scale. It is not static. It is a living number, designed to evolve as new data arrives. And with 3I Atlas, the most important data is yet to come. Imagine the score fluctuating in the coming weeks and months. If 3I Atlas reemerges from behind the Sun, and astronomers detect a non-gravitational acceleration that cannot be explained by the observed outgassing, a ghostly push like Oumuamua's that bumps the score up significantly. If the James Webb Space Telescope were to detect narrow-band emissions in specific patterned frequencies coming from the object, that would be a huge bump, potentially pushing it into the high 7s or even 8s. Conversely, the score can also drop. If the object's post-conjunction orbit fits perfectly with gravity alone, if the amount of water vapor increases as it heats up, and that bizarre 8:1 ratio begins to normalize if the iron emission lines appear right on schedule as predicted by natural heating models, then the score drops. It might fall to a 3 or even a 2. It would still be a weird comet, a valuable scientific curiosity, but the case for its natural origin would be overwhelming. So, what would it take to push the score to a 9 or a 10? To end the debate? That is the territory of the smoking gun. You would need unambiguous evidence of technology that could not, under any physical scenario we understand, be a natural object. Imagine if 3I Atlas suddenly began emitting a repeating coded radio signal, not the random noise of a natural cosmic source, but a clear, structured pattern. That is a 9, maybe even a 10, depending on the content of the message. Or imagine if, through some miracle, a future spacecraft intercept mission, like the proposed Juno flyby we'll discuss later, were to capture high-resolution images that resolved angular features, flat surfaces, or modular structures. That is a 10. Game over. We are not alone, but we are not there. We are not even close. And it is absolutely critical to understand what the official space agencies, NASA and the European Space Agency, are saying publicly. Amidst the storm of media hype, their position has been conservative, cautious, and scientifically correct. NASA has explicitly stated that 3I Atlas is, for now, considered to be a natural comet, pending any evidence to the contrary. They have rightly pushed back against the overhyping of alien probe claims, emphasizing that while the observations are unusual, they are not yet inconsistent with the known, if diverse, behavior of comets. This is the bedrock of the scientific method. Extraordinary claims require extraordinary evidence. The burden of proof rests squarely on the shoulders of the "this is technology" hypothesis, not the other way around. Comets, even weird ones, are common. Visiting alien spacecraft are, as far as we know, non-existent. So why are we even having this conversation? Because the evidence is accumulating in a way that makes the natural explanation feel less and less comfortable over time. It is not impossible, just less satisfying. And because we are about to lose our view. A solar conjunction is a hard deadline. When we can see it again in late November, the picture will either become much clearer or infinitely more confusing. This is how you, as an engaged observer of this unfolding story, can watch the score evolve for yourself. Track these key signals in the coming months. 1. Astrometry. Does its position after the blackout match the predictions based purely on gravity? Or are there tiny deviations that hint at thrust? 2. Spectroscopy. Does its chemical composition change as expected with solar heating? Or does it remain stubbornly anomalous? 3. Light curve. Does its brightness vary in predictable ways? Or are there irregular spikes or dips that suggest something else is going on? These are the data points that will move the needle on the Loeb scale, and they are all testable, falsifiable predictions. That is the beauty and the power of science. You make a hypothesis, you take a measurement, and you allow reality to tell you if you are right or wrong. Right now, 3i Atlas sits in the uncomfortable, thrilling middle of the Loeb scale. It is anomalous enough to command our attention, but not anomalous enough to overturn the natural hypothesis. But with a critical observational gap just around the corner and the tantalizing possibility of new data from Mars orbiters and a potential Jupiter flyby, this story is far from over. It is a cosmic mystery, and for the first time, we have a way to keep score. But as we stand here, weighing the evidence, a skeptical voice rightly asks, aren't we just fooling ourselves? Aren't we just noticing the weird ones because they're weird? Let's confront that question head on. Let me ask you a question. A simple one. If you flipped a coin 10 times, and it came up heads every single time, what would you think? Your first reaction would likely be disbelief, followed by suspicion. You'd probably check the coin, wouldn't you? You'd want to make sure it wasn't a trick, that it had a tail side. Why? Because while it is possible for a fair coin to land on heads 10 times in a row, the odds are 1,000 to 1 against it. It is so improbable that our minds instinctively reject randomness as the sole explanation. We start looking for a hidden mechanism, a pattern, a reason. We start looking for a form of intent. This is the very heart of the dilemma we face with 3i Atlas. We are confronted with a series of events, its trajectory, its timing, its chemistry, that when viewed together, feel like 1,000 to 1 long shot. It feels like a miracle. And in science, when you are faced with what looks like a miracle, your job is to investigate the math. You must ask the hard, skeptical question. Are we witnessing a genuine statistical improbability? A true cosmic coincidence? Or are we just fooling ourselves, falling victim to our own pattern-seeking brains and a phenomenon known as selection bias? This is the strongest and most important counterargument to the alien probe hypothesis. So let's give it the respect it deserves. Selection bias, in simple terms, is our tendency to notice things that are unusual while ignoring the vast, silent majority of things that are normal. Imagine you're standing on a beach, looking for interesting seashells. You walk for miles past millions of perfectly ordinary, boring shells. Then, you find one that is bright pink and perfectly spiral-shaped. You would rightfully be amazed by it. But it would be a mistake to conclude that all seashells are pink and spiral-shaped. You noticed it because it was an outlier. The thousands of interstellar objects that might be passing through our solar system, far away and undetected, are the boring seashells. We've only just built the tools, the powerful survey telescopes like Atlas, that allow us to spot the occasional pink one. The fact that the first few we've found are weird doesn't necessarily mean they're all weird, or that their weirdness is artificial. It might just mean that our nets are, for now, only catching the oddballs. It is a fair and powerful point. But here is the counter-argument to the counter-argument. As we've established, we have only ever detected 3 interstellar objects. Ever. Out of that minuscule sample size of 3, 2 of them, Oumuamua and 3, Atlas, are profoundly strange in completely different ways. If we had detected 100 interstellar objects, and 98 of them were normal comets, like Borisov, then the 2 weird ones would be easily dismissed as the expected statistical outliers. But when 2 out of your first 3 data points are screamingly anomalous, it is not a robust statistical trend, but it is a curiosity that demands we pay closer attention. It suggests that the interstellar population might be far more diverse and far stranger than we ever imagined. So, let's try to do the math, even if it's just a thought experiment. Could we actually calculate the odds that a random interstellar object would arrive with this specific geometry, this specific timing, and this specific chemistry? Let's try to build a model of the improbability. First, let's revisit that ecliptic alignment. As we discussed, the ecliptic plane is a very thin slice through the vast, 3-dimensional space of the celestial sphere. If you assume that interstellar objects arrive from truly random directions, the probability of any single one of them arriving within that narrow, 5-degree slice of our solar system's highway is approximately 1 in 36. That is just basic spherical geometry. So, you'd expect about 1 in every 36 interstellar visitors to have a low inclination like this. Those are not impossible odds, but it's not common either. And since we've only found 3, it is a bit like playing a 36-sided die and hitting the number 1 on your very first try. Lucky, but plausible. Now, let's layer on the timing. The object reaches perihelion, its moment of peak activity, right at the start of the solar conjunction, that weeks-long window when Earth loses its line of sight. Is that a coincidence? Well, solar conjunctions are a predictable part of orbital mechanics. Any object that passes close to the Sun will, at some point, be on the opposite side from Earth. And for most comets, peak activity naturally happens near perihelion when the solar heating is strongest. So, in one sense, it is expected that these 2 events would overlap. But the fact that it is a prolonged, 4-week conjunction, perfectly bracketing the most scientifically interesting period, does feel remarkably convenient. If you were a mission planner aiming for stealth, this is the window you would choose. Let's think about this a different way. Let's run a mental simulation, a Monte Carlo experiment. Imagine you could create a computer program that generates 10,000 random interstellar trajectories. You give them random inclinations, random entry velocities, random orientations. You then ask the computer, how many of those 10,000 random trajectories manage to satisfy all of these conditions simultaneously? 1. They pass within 5 degrees of the ecliptic. 2. They reach perihelion during the specific weeks of Earth's solar conjunction. 3. They also happen to come within a reasonable observational distance of both Mars and Jupiter within a 6-month span. While I can't run the actual simulation here, a rough back-of-the-envelope calculation based on geometric probability suggests that the number would be incredibly small. My guess is somewhere between 0.1% and 1%. That means that maybe only 1 in 100, or perhaps as few as 1 in 1,000, random interstellar objects would naturally hit all of those specific waypoints with that specific timing. That sounds incredibly rare. And if you believe that detectable interstellar objects are themselves rare, then witnessing such an event becomes a truly profound coincidence. However, if you believe the estimates, based on Oumuamua's discovery, that there could be thousands of interstellar objects passing through the wider solar system every single year, most too faint for us to see, then the odds change. If you roll the dice thousands of times a year, eventually you are going to get snake eyes. The problem is, we are not seeing a few of these per century. We are seeing one. It's happening right now. And it also happens to have that bizarre, hard-to-explain chemistry and those unusual metal emissions layered on top of the weird geometry. The coincidences are multiplying. Let's compare this to our other two data points. Oumuamua had a wild orbital inclination of about 122 degrees. It came in steep, passed through, and left steep. Its trajectory was definitely not aligned with our highway. But it had its own profound mystery, that non-gravitational acceleration. Borisov had an inclination of about 44 degrees, also tilted, and was chemically normal. So what we have is not a repeating pattern. We have three visitors, each one telling a completely different story. One was normal, one was weird in its motion, and this new one is weird in its geometry and its chemistry. This diversity makes it very difficult to claim a pattern, but it also makes it difficult to dismiss the strangeness of 3I Atlas as just business as usual for interstellar objects. The alternative hypothesis, of course, is that this isn't a coincidence at all. It is targeting. If 3I Atlas is an artificial probe, its trajectory would not be random. It would have been deliberately and precisely chosen to optimize a survey of our solar system. A low inclination would be chosen to stay in the plane where all the planets are. The timed conjunction would be chosen to avoid observation during a critical phase. And the sequential flybys of Mars and Jupiter would be chosen for data collection. From a mission design standpoint, this is exactly what you would plan. And this is where we must exercise our intellectual honesty. With the data we currently have, we cannot definitively distinguish between natural object with incredibly lucky geometry and designed object with optimal geometry. The math alone does not give us enough leverage to make a final call. The trajectories are consistent with both hypotheses. So, what would break this deadlock? What would give us the power to firm up the odds and make a real statistical judgment? The answer is simple: more data. We need more interstellar objects. The Vera C. Rubin Observatory, currently under construction in Chile, is poised to revolutionize this field. When its legacy survey of space and time comes online in the near future, it is expected to detect not one or two, but dozens, perhaps hundreds of interstellar objects over the next decade. For the first time, we will finally have a real statistical baseline. We will know what typical looks like for an interstellar visitor. We will know how often low-inclination arrivals really happen. And then, and only then, we will be able to say with confidence whether 3I Atlas is genuinely anomalous, or if it was simply the first one of its kind that we happened to notice. Until then, we are stuck here, in this uncomfortable and fascinating place, wrestling with small number statistics and probabilities that feel both tantalizing and unsatisfying. But I will leave you with this final thought on the matter. Coincidence is an idea that makes our brains emotionally uncomfortable. When something rare happens at a convenient time, in a convenient way, every instinct we have screams, not random. But we must remember that rarity is not, by itself, evidence. Improbability is not, by itself, proof. Things that are one in 1,000 happen. They have to happen to someone somewhere at some time. The question we are now faced with is, are we that someone? Did our civilization just happen to be the one that spotted the 1 in 1,000 weird interstellar object? Or is our 1 in 1,000 probability calculation itself wrong, because we have failed to consider a variable that changes everything? Intent? The math cannot tell us yet, but the clock can. Because in less than 1 month, 3I Atlas will slip behind the sun. It will disappear into the glare, and we will be blind. And if a course change is going to happen, if any definitive evidence of artificiality is going to manifest itself, that blackout window is when it matters most. It is the silence before the sun. And that is what we must face next. There is a unique and primal kind of suspense that comes from knowing you are about to lose sight of something important. It is that heart in your throat feeling you get when you see a child wander out of sight in a crowded store, or when a car driving erratically disappears around a blind corner. You can't see them. You can't track them. You are plunged into a sudden state of helpless ignorance. All you can do is wait, holding your breath, hoping and praying that when they reappear, everything is still normal. We, as a planet, are about to experience that exact feeling on a cosmic scale. 3I Atlas is about to disappear around a blind cosmic corner, and it is going to stay hidden from our view for weeks. This event, the solar conjunction, is not a speculative theory or a dramatic flourish. It is a predictable, unavoidable celestial alignment. But in the context of this unfolding mystery, it has become the most suspenseful and highest stakes waiting game in modern science. So let me walk you through the timeline and the geometry of this impending blackout, because this is where the stakes become terrifyingly real. The clock is ticking. The critical period begins in late October 2025. Around October 25th, the angular separation between 3I Atlas and the Sun, as seen from our vantage point on Earth, will shrink to less than 50 degrees. That number is a critical threshold. It is the strict sun avoidance limit for the Hubble Space Telescope. If Hubble were to point any closer to the Sun, its sensitive instruments, its delicate electronic eyes, would risk being permanently fried by the intense radiation and heat. So, on that day, our sharpest eye in the sky goes dark on this target. One by one, other great observatories will follow suit as the angle continues to shrink. By October 29th, the day it reaches perihelion, the geometry becomes impossible. A comet will be, for all intents and purposes, in the same patch of sky as the Sun. It won't be a perfect eclipse. It won't pass directly in front of the solar disk, but it will be so. Closed at the Sun's incandescent, overwhelming glare will completely drown out the faint light of the comet. It will be like trying to spot a single firefly hovering next to a searchlight. Ground-based optical telescopes will lose the object completely in the solar halo. This total blackout period will extend all the way through late November. The exact date that observations can resume will depend on when the Sun-object-Earth angle widens back out beyond the safe viewing thresholds for our telescopes. But the European Space Agency and NASA have both indicated that late November is the earliest re-emergence window. So let's be clear about the timeline. We are looking at roughly 4 weeks, 28 days, nearly a month where the most active, the most interesting, and the most profoundly anomalous interstellar object we have ever tracked will simply vanish from our view. Now, let's talk about why this 4-week window is so tactically perfect if, and this remains the central, tantalizing if, something artificial is at play. Imagine for a moment that you are the commander of an advanced, autonomous reconnaissance probe. Your mission is to enter a new, potentially inhabited star system. Your objectives are to study the inner planets, to gather data on their atmospheres and magnetic fields, perhaps even to deploy smaller, secondary instruments or sensors for more detailed analysis. But you have a prime directive. You must do all of this while minimizing the chance of being detected, tracked, or understood by any observers on the third planet, which your initial scans have shown to be teeming with a curious and technologically capable species. What do? You would not come blazing in at a random angle. You would approach along their system's main highway, the ecliptic, to make your trajectory seem as natural as possible. You would time your closest approach to their star, your moment of maximum power generation and peak activity, to coincide perfectly with a period when the dominant intelligent species on that third planet cannot observe you. You would use their own star as a shield. You would make your most critical moves during the solar eclipse of their awareness. Avi Loeb, in multiple interviews and essays, has repeatedly called this the perfect time to maneuver. If 3I Atlas were going to do anything to betray its artificial nature, if it were going to fire a thruster to adjust its course, if it were going to deploy smaller probes, if it were going to reconfigure its structure, the solar conjunction window is the absolute ideal time to do it. By the time our observatories on Earth regain their line of sight in late November, the deed would be done. The object would be on a new and unexpected trajectory. But without the continuous tracking data from the blackout period, astronomers would have a much harder, though not impossible, time proving exactly when, where, and how that change occurred. The evidence of the maneuver itself would be lost in the darkness. Now, let me be absolutely clear. This is speculation. This is a what-if scenario. There is currently zero direct evidence that 3I Atlas possesses any maneuvering capability. There is no evidence it is going to do anything during the conjunction, other than what a normal comet would do: continue on its predicted orbital path outgas naturally as it is superheated by the sun, and then begin to cool down as it moves away. The default scientific assumption, the null hypothesis, is that nothing unusual will happen. But the timing makes you think. So can we observe it at all during this blackout? Is there any way to peek behind the cosmic curtain? The short answer is, barely and only indirectly at best. There are instruments called solar coronagraphs, like those on the SOCO spacecraft, which are designed to study the sun's faint outer atmosphere, the corona. They work by blocking out the bright disk of the sun, and in the process, they have discovered thousands of sun-grazing comets that pass incredibly close to the solar surface. But 3I Atlas is not a sungrazer. Its perihelion of 0.96 astronomical units keeps it well outside the field of view of these instruments. So, coronagraphs are probably a dead end. There are other, more speculative techniques, like looking for subtle disturbances in radio signals from other spacecraft as they pass behind the sun. But 3I Atlas is too small and not a radio emitter, so this is also unlikely to help. The stark reality is this: during the conjunction, we are effectively blind. But what we can do, and what makes the post-conjunction observations so incredibly critical, is prepare. Right now, teams of astronomers around the world are planning their campaigns. They are booking telescope time. They are refining their models. They are preparing to scrutinize 3I Atlas the absolute moment it re-emerges from the glare. And they know exactly what they are looking for. They have a checklist. 1. Light curve continuity. Did the object's brightness evolve as our models of solar heating predict? Or were there sudden, inexplicable jumps or drops in its light that could suggest a structural change, a fragmentation event, or a sudden, massive release of material? 2. Spectroscopy. Is the carbon dioxide to water ratio still a bizarre 8:1? Or has it started to shift toward a more normal, water-dominated composition as deeper layers of ice are exposed? And critically, does iron finally appear alongside the nickel as the natural heating models predict? 3. Position residuals. This is the big one. Does the object as observed position in the sky match the predictions based on a purely gravitational trajectory? Or are there discrepancies, what astronomers call residuals, that suggest an unknown force has acted upon it? This would be the clearest evidence of acceleration, of a maneuver. 4. Morphology. Does it still look the same? Has the structure of its coma or tail changed in unexpected ways? Are there any new jets, asymmetries, or features that simply were not present before it went behind the sun? These are all testable, quantifiable metrics, and the answers will start pouring in within days, or even hours, of the object's reappearance in late November. But here is the thought that keeps people like Avi Loeb, and frankly, a growing number of professional and amateur astronomers up at night. If something does happen during that 4-week blackout, we will only ever find out after the fact. We will see the evidence of the event, but we will not have witnessed the event itself. It is like arriving at a crime scene and trying to reconstruct what happened based only on the forensics. You can make strong, compelling inferences, but you will never have the video footage. The timing of the Mars and Jupiter flybys adds another layer of profound intrigue to this celestial chess game. On October 3rd, just before the main blackout begins, 3I Atlas passes Mars. The European Space Agency will be watching with its orbiters, trying to get a precious data point from a different vantage point, a form of triangulation. Then, in March 2026, it passes Jupiter, where we might, if we're incredibly lucky, have another chance to observe it from the perspective of the Juno spacecraft. It's a choreographed sequence of opportunities. Let me address the fear factor directly, because I know what some of you are thinking. What if it does something hostile during the blackout? Let me reassure you, NASA and the European Space Agency have been unequivocal. 3I Atlas poses no threat to Earth. The geometry of its orbit makes an impact impossible. Even if it were to break apart into 1,000 pieces during perihelion, those pieces would continue on the same basic trajectory and would not intercept Earth's orbit. The closest it gets is over 160 million miles away. There is no impact risk, period. The realistic worst-case scenario isn't danger. It is ambiguity. It is the possibility that something strange happens during the blackout, and we are left arguing for decades about whether it was a natural outgassing event or something else, without the continuous data to definitively settle the debate. And that is the true power and the true frustration of solar conjunctions. They are not just observational inconveniences. They are gaps in the historical record. We can try to interpolate across them, but we can never rewind the tape and watch what actually happened in the dark. So, what happens next? In less than 4 weeks, 3I Atlas will cross behind the sun and go silent. We will wait. We will monitor what little we can. We will prepare our instruments. And then, in late November, we will look. If the object reappears exactly where we expect it to be, behaving exactly as a comet should, then the score on the Loeb scale will likely drop. Coincidence will remain the most plausible explanation, and we will chalk this up to an unusually weird, but ultimately natural visitor from the stars. But if there are surprises, if the position is off, if the chemistry has shifted in unexplained ways, if new features have appeared, then the questions will deepen, the score will rise, and the hypothesis that we are looking at something far more profound than a comet will gain a weight it has never had before. The silence before the sun is almost here, and when that silence finally breaks, we will know more. Maybe not everything, but more. And this brings us to the most speculative, the most science-fictional, and yet the most tantalizing idea of all. What if 3I Atlas isn't a single object? What if it's a carrier? Let me be absolutely clear right from the start. What we are about to discuss is speculation. This is not established science. This is not a proven theory. This is a hypothesis, a thought experiment, an exercise in pushing the boundaries of what we consider possible. It is an idea that A.V. Loeb and a few other bold thinkers have explored in the context of interstellar objects. And it is a hypothesis that has gained a renewed whispered attention with the arrival of the profoundly strange 3I Atlas, but it is not proving. It is a framework for thinking about what signs we would need to look for if an interstellar visitor were something more than just a monolithic chunk of ice and rock. This is the Mothership hypothesis. The idea is as simple as it is audacious. What if some interstellar objects are not single monolithic bodies, but are instead carriers? What if they are vast, dormant vessels designed for the sole purpose of traversing the crushing, empty immensity of the gulfs between the stars, protecting a precious cargo within? And what if that cargo consists of smaller probes, instruments, or sensors that can be deployed upon arrival at a target star system? Think of it as the cosmic equivalent of a deep-sea exploration vessel, like the Calypso, arriving at a coral reef and launching smaller, more nimble submarines to survey the environment up close. Loeb first began to popularize versions of this idea in the wake of Oumuamua's baffling passage. He suggested that Oumuamua itself might not have been a probe, but perhaps a piece of a larger technological object that had broken apart, or that it could have deployed smaller dust-sized probes that we simply didn't have the capability to detect. The mainstream scientific community was, to put it mildly, deeply skeptical. But the hypothesis was never really about Oumuamua specifically. It was about establishing a search framework. If advanced interstellar probes exist, what would they look like? How would they behave? What breadcrumbs would they leave behind for us to find? It was a call to start thinking, in a rigorous, scientific way, about how to search for extraterrestrial artifacts, not just radio signals. Now, with 3I Atlas, some of those very same questions are resurfacing, not because we have any proof, but because the object's peculiar collection of anomalies seems to fit the profile. Its behavior doesn't just invite the question, it practically screams it. So, let's engage with this thought experiment. If 3I Atlas were a carrier, a mothership, what specific observable signs might we expect to see? First, you might look for short-lived micro-brightness spikes. If the main object were releasing smaller secondary objects, probes, sensors, whatever you want to call them, those deployment events might cause brief localized flashes of light as new reflective surfaces are exposed to sunlight, or as trapped materials or gases vent into space. These spikes would be incredibly subtle, possibly lasting only for minutes or hours. They would also be incredibly difficult to distinguish from the normal, chaotic jet activity of a natural comet. You would need a dedicated, high-cadence monitoring campaign, with telescopes taking pictures every few minutes, not just every few hours, to have any hope of catching one of these fleeting events and distinguishing it from natural outgassing. Second, you could look for unusual radar or specular reflections. Natural comets are, for the most part, rubble piles. They are rough, porous, irregular bodies covered in a thick layer of dark organic dust. When you bounce a radar signal off a comet, it comes back in a diffuse, scattered, and very weak way. But what if part of 3I Atlas had smooth, flat, metallic surfaces? Unlikely for a comet, but very likely for a piece of technology. If a radar beam from a facility like the Goldstone Deep Space Communications Complex were to hit such a surface, you might see an unexpectedly strong, mirror-like, or specular radar return. It would be like shining a flashlight at a lump of coal versus shining it at a mirror. To my knowledge, we have not yet attempted radar observations of this object, but it is something that could, and should, be attempted when it re-emerges from behind the sun. Third, you might search for a post-conjunction debris train. If a series of probes were to be deployed during the solar blackout window, they might not all disperse immediately. They might form a temporary, linear structure of smaller, fainter objects trailing behind the main body, like a string of pearls following a ship. These would eventually show up in our wide-field imaging as faint, secondary sources of light. Now, the major challenge here is that natural comets can, and often do, fragment. The thermal and gravitational stresses of a close pass to the sun can cause the nucleus to break apart, producing a natural debris train. Distinguishing between a natural breakup and a deliberate deployment from our immense distance would be incredibly tricky, perhaps impossible, without extremely detailed tracking of each individual fragment. Now, let's revisit the previous clues we've discussed, but this time, look at them through the lens of the mothership hypothesis. Remember Loeb's claim of a forward glow? Those headlights? In this context, it could be speculatively reinterpreted as the signature of active thermal management. If 3I Atlas were an artificial craft using the sun's intense heat to power its internal systems, you would expect its sunward face to get incredibly hot. And if that face were deliberately venting a gas like carbon dioxide to act as a radiator, to control its temperature and shed that waste heat, you would see exactly the kind of bright, directional, focused emission that Loeb described. This is also where that bizarre 8-to-1 carbon dioxide to water ratio suddenly clicks into place with a chilling sense of engineering logic. As we've discussed, carbon dioxide is a far more practical and efficient coolant for a spacecraft than water. It sublimates at lower temperatures, it's easier to handle, and it doesn't have the same inconvenient freezing properties. So, a spacecraft using a passive thermal management system, venting CO2 to stay cool as it approached a star, would produce a chemical signature that looks a lot like what the James Webb Space Telescope and Spherix observed. The emphasis, of course, must be on would look like. This is not proof. This is pattern matching, but the pattern is undeniably compelling. And finally, let's talk about the nickel. The detection of strong nickel emission without its cosmic twin, iron, is one of the most chemically peculiar aspects of this entire mystery. The natural explanations, like organometallic compounds, are plausible but exotic. But what if the nickel is not a natural component of the object itself? What if it is process effluent? What if it is an industrial byproduct, the incidental exhaust from whatever advanced systems are operating inside the object? Nickel-bearing compounds, particularly carbonyls, are used in certain highly specialized industrial processes on Earth, such as purifying nickel or fabricating precision components. While they are often toxic and volatile, who knows what engineering solutions an advanced civilization might develop? If internal heat sources or chemical reactions were breaking down specific nickel-bearing materials as part of a power generation or manufacturing process, you would release nickel atoms into the surrounding coma. And if those materials did not include comparable amounts of iron, you would get the exact nickel without iron signature that we are seeing. Again, this is highly speculative, but it is not physically impossible. So why would a mothership favor the solar conjunction window for deploying these probes? For the same reason, a military force favors the dark of night for a covert operation. You do it when you are least likely to be observed. If you are deploying secondary objects, whether they are passive sensors designed to fall toward the inner planets or active probes capable of changing their own course, you want to do it when ground-based tracking is at an absolute minimum. The solar conjunction provides the perfect 4-week window of opportunity. Now, let's pump the brakes and be good scientists. We must rigorously consider the counter-arguments because they are strong and they keep us grounded in reality. First, as we've noted, dust jets and phase effects can explain a lot. Comets are messy, chaotic, and asymmetric. Localized vents of gas and dust from active regions on the nucleus can absolutely create forward-facing jets that look directional and bright. The complex interplay of how sunlight scatters off different-sized dust grains at different viewing angles can produce all kinds of optical illusions. Before you are allowed to invoke alien spacecraft, you must exhaust every possible mundane explanation. And we have not done that yet. Second, carbon dioxide-rich comets do exist. They are rare, but not unheard of. Comet C 2016 R2, Pan-STARRS, was a famous outlier, an object with an unusually high abundance of carbon monoxide and carbon dioxide, likely because it formed in a particularly frigid region of its birth system. Weird chemistry happens naturally in the cosmos. It is the exception, not the rule, but exceptions are not impossible. Third, fragmenting comets are common. It is a very real possibility that 3I Atlas will not survive its close pass to the Sun. The intense thermal stress and the Sun's powerful tidal forces could tear it apart, causing it to disintegrate in a process that is entirely natural. If that happens, it will produce a swarm of debris. That debris will not be probes. It will be chunks of ice and rock. And as we've said, Distinguishing between this natural fragmentation and a deliberate deployment from our Earth-based vantage point alone will be nearly impossible without incredibly detailed, long-term tracking. So, what would constitute real, observable consequences if the carrier hypothesis were true? What is the smoking gun we should be looking for? The most definitive piece of evidence would be anomalous accelerations after the conjunction. If 3I Atlas, or any of its potential companion objects, reappears on a trajectory that does not match a purely gravitational orbit, if there are position residuals that cannot be explained by natural outgassing or radiation pressure, it would be a profound discovery. It would mean thrust. It would mean control. Another, more speculative possibility is transient meteor entries. If small, millimeter or centimeter-sized probes were deployed, and some of them happened to enter Earth's atmosphere, they would produce meteor events. But here we must be extraordinarily careful not to fall into the trap of sensationalism. The Earth is constantly bombarded by tens of thousands of natural meteoroids every single day. A handful of unusual meteor reports during or after the conjunction would, by themselves, prove absolutely nothing. You would need coordinated observations from multiple professional meteor camera networks, with precise trajectory reconstructions that could clearly and unambiguously link the incoming meteors back to the path of 3I Atlas. This is technically doable, but it requires immense scientific discipline and a very high burden of proof. This brings us to the greatest risk we face in this entire endeavor, pareidolia. The human brain is a pattern-making machine. We are wired to see agency, purpose, and familiar shapes even in random data. We see faces in clouds. We see a man in the moon. We hear messages in static. When we are primed by a compelling story to look for alien probes, we will be tempted to find them, even if we are only looking at chunks of ice. The history of astronomy is littered with false alarms, from Percival Lowell's canals on Mars to the WOW signal that was never repeated. We have to guard with every ounce of our scientific integrity against fooling ourselves. So how do we do that? You pre-register your predictions. You state in advance what specific measurements would confirm or falsify your hypothesis. You do not retrofit your explanations to the data after the fact. You let the data lead you, not your expectations. The Mothership hypothesis is exactly that, a hypothesis. It is testable. It makes predictions. And if those predictions fail, if the post-conjunction data show no evidence of deployment or maneuvering, then the hypothesis should be discarded with rigor and discipline. But here is the uncomfortable, thrilling part. If it is not discarded, if the data that comes back in late November shows features that are consistent with deployment, with maneuvering, with active technology, then we will find ourselves in truly uncharted territory. Because at that point, we would no longer be talking about a weird comet. We would be talking about something that chose to come here. And that brings us to a fascinating historical question. Has this tactic, hiding behind the sun to conduct operations in secret, ever been done before? Not by interstellar visitors, but by us. Have human space missions ever used solar conjunctions for operational advantage? As it turns out, the answer is yes. And the playbook is very well established. The idea of using the sun as a cosmic shield, a place to hide and maneuver while your adversary is blind, sounds like a tactic straight out of a science fiction battle. But it is not fiction. Solar conjunction isn't just a quirky astronomical event. It is a hard operational reality for any species that dares to send its machines into the solar system. For decades, the engineers and mission planners who guide our own robotic emissaries have had to contend with this celestial blind spot. They have learned to work around it, to plan for it, and in some very clever cases, to even exploit it. The history of our own space exploration provides a fascinating and very human playbook for the kind of cosmic hide-and-seek that might be at play with 3I Atlas. The classic and most routine example of this is our ongoing exploration of Mars. every 26 months like clockwork. The orbital paths of Earth and Mars align in such a way that Mars passes directly behind the Sun from our perspective. For the duration of this Mars-solar conjunction, which typically lasts for about 2 weeks, our ability to communicate with our robotic family on the Red Planet, the rovers, the orbiters, the landers, becomes unreliable at best and completely impossible at worst. The reason for this is the Sun's corona. This is not the calm, steady star we see in our sky. The Sun's outer atmosphere is a roiling, chaotic soup of charged particles and powerful, tangled magnetic fields. When we try to send a radio signal through this turbulent environment, the signal gets scattered, distorted, and corrupted by the plasma. It's like trying to have a clear conversation in the middle of a hurricane. You can sometimes shout a few words through, but the message is likely to be garbled and misunderstood. For a multi-billion-dollar robotic mission, garbled and misunderstood is a recipe for disaster. A single corrupted command could send a rover driving off a cliff or an orbiter firing its thrusters at the wrong time. So NASA and the European Space Agency have a standard, well-practiced protocol. During Mars-solar conjunctions, the missions go into a state of digital hibernation. The rovers stop driving. They park in a safe location and run only minimal, pre-programmed operations. The orbiters continue their scientific observations, but instead of transmitting the data back to Earth in real time, they store it on board in their solid-state memory. Then, once the conjunction ends and a clear, clean line of communication is restored, the massive backlog of data gets downloaded and normal operations resume. This is a forced blind spot. Mission controllers on Earth hate it. They are temporarily cut off from their charges, flying blind for 2 weeks, losing that vital, real-time awareness. But it is an unavoidable consequence of the celestial mechanics that govern our solar system. Even the heroic Apollo missions to the Moon faced a similar challenge, though their shield was not the Sun, but the Moon itself. During every single orbit of the Moon, the Apollo spacecraft would pass behind the lunar far side, and for those periods sometimes lasting for half an hour or more, all radio contact with Earth would be completely cut off. The solid rock of the Moon itself physically blocked the signals. In those tense, silent minutes, the astronauts were the most isolated human beings in history. Mission Control in Houston could not see their telemetry. They could not talk to them, and they could not help if something went wrong. It was a period of absolute radio silence. And it was during one of these far-side passes on the daring Apollo 8 mission, the first time humans had ever left Earth's orbit and traveled to the Moon, that the astronauts had to perform their most critical maneuver, the engine burn that would break them out of lunar orbit and send them on their trajectory back home. Think about the tension of that moment. The entire world was holding its breath, and Mission Control had no idea if the burn had even started, let alone if it had succeeded, until the spacecraft finally reappeared from behind the edge of the Moon. That predictable, routine blackout added an almost unbearable layer of suspense to an already nerve-wracking operation. Now, let's talk about the classified side of things, because this is where the geometry of space becomes not just an inconvenience, but a strategic tool. The world's military and intelligence agencies operate vast constellations of satellites with the constant awareness that they are being watched. If you are running a reconnaissance satellite, you care very deeply about who can see you and when. Certain orbits, like geostationary orbits, where a satellite remains over a single point on Earth, make them highly predictable targets for optical and radar tracking from the ground. A rival nation can, with relative ease, monitor your spacecraft's activity, learn its capabilities, and even predict its movements. So if you need to perform a sensitive operation repositioning the satellite, deploying a new piece of hardware, or performing a maneuver you don't want your adversary to analyze, you use the geometry of the Earth and the Sun to your advantage. You can time your maneuvers to occur when your adversaries' ground-based tracking stations are on the wrong side of the planet and do and have a direct line of sight. You can perform them during local daylight, when the bright sky makes optical observation from the ground impossible. Or, for the ultimate in stealth, you can use the sun itself. You can position your spacecraft such that, from the perspective of the watchers on Earth, it is so close to the sun's blinding glare that their telescopes simply cannot see it. This is not speculation. This is basic orbital mechanics and a fundamental principle of operational security in space. Geometry is used as both a weapon and a shield. Now, does this history prove that 3I Atlas is using this tactic? Absolutely not. But what it does prove is that the tactic itself is sound. It has precedent. It demonstrates that if an object possessed control, if it were artificial and deliberately navigating, then choosing to perform a critical maneuver during a solar conjunction would be an operationally brilliant and entirely logical move. But let's think about the feasibility. Could an object actually hide its maneuvers completely during a solar conjunction? The answer is yes and no. Any large, powerful engine burn, what engineers call a high delta V maneuver, produces an enormous amount of heat. Chemical rocket engines are incredibly hot. Their thruster plumes glow with intense infrared radiation. If 3I Atlas were to fire a large chemical rocket during the conjunction, there is a chance that our own space-based surveillance assets, our infrared space telescopes, or even the classified early warning satellites designed to spot missile launches might detect the thermal flash. If something big and hot happened, someone somewhere on Earth might see it, even if our ground-based telescopes could not. But what about a small, subtle, and efficient burn? What about a cold gas thruster that uses the venting of compressed nitrogen or even carbon dioxide to produce a gentle, continuous push? Such a system could be incredibly subtle. And if the thrust were directed away from the Earth and other major observing assets, its faint thermal signature could easily be lost in the noise of the solar system. The other major constraint is astrometry. As we've discussed, even if you can't watch an object during the conjunction, you can precisely measure its position before it goes in, and precisely measure it again the moment it comes out. Orbits do not lie. If 3I Atlas re-emerges in late November, and its position in the sky has not perfectly matched the predicted gravitational trajectory, that is hard physical evidence that an acceleration occurred. The exact timing of the burn would be uncertain. We would only know that it happened sometime during that 4-week gap, but the fact of the maneuver would be clear. So, could a maneuver be completely hidden? Partially. The thermal signature of a subtle burn might escape our notice, but the gravitational fingerprint of that burn would remain. It would be imprinted on the object's ephemeris, the table of its predicted future positions. The post-conjunction astrometry will either match the predictions or it will not. There is no faking that. This brings us to a very important point. Even if something were to maneuver during the blackout, we would still have the evidence afterward. We would not have the video footage, but we would have the forensic evidence. And in science, the forensics are often more than enough. The behind-the-sun tactic is real. It is understood. It has been used, but it is not magic. It buys you operational secrecy in the moment, but it does not grant you immunity from eventual detection. In the case of 3I Atlas, however, its chemistry might ultimately be a bigger tell than its trajectory. Because if the object is venting all of that carbon dioxide as part of some internal thermal or propulsion system, that is a continuous signature. It is not something you can easily turn on and off or hide. It is baked into the very spectrum of the object. And this brings us full circle, right back to the central chemical mystery. Why is this thing venting so much CO2? Why is the ratio 8:1? And what does that tell us about what 3I Atlas truly is and where it came from? To answer that, we must now dig deeper into the carbon dioxide data itself, because this is the very ground where the natural and the artificial explanations collide most directly. If you have ever tried to read a professional scientific paper on cometary chemistry, you know that it can feel like trying to decipher an alien language. The pages are a dense forest of jargon, absorption lines, emission bands, column densities, abundances. It is a world of incredible complexity and precision. But buried deep within that jargon, hidden in the meticulous data tables from the James Webb Space Telescope, is one of the single most important and baffling clues we have in the entire mystery of 3I Atlas. So, let me be your translator. Let's push past the technical terms and get to the heart of what our most powerful telescope saw, because it is a discovery that challenges the very definition of what a comet is supposed to be. The date is August 6th, 2025. The magnificent James Webb Space Telescope, a beacon of human ingenuity orbiting 1,000,000 miles from Earth, turns its golden mirror towards our interstellar visitor. It engages two of its key instruments, the near-infrared spectrograph, (NIR-SPEC), and the mid-infrared instrument, MIRI. These are not cameras that take pretty pictures. They are cosmic prisms of unimaginable power. They capture the faint, invisible infrared light from the comet and break it down into its constituent wavelengths, creating a chemical fingerprint, a spectrum. Different molecules in the comet's coma water, carbon dioxide, carbon monoxide, vibrate and glow at very specific infrared wavelengths when they are excited by sunlight. By reading these signatures, the James Webb can tell us, with stunning accuracy, exactly what the comet is, breathing into space. The results, released to a stunned scientific community on August 25th, were strange from the very first glance. The telescope detected a powerful, blazing emission line at a wavelength of 4.3 micrometers. That is the unmistakable textbook signature of carbon dioxide. Carbon dioxide. Finding CO2 in a comet is perfectly normal. But what was not normal, what was, in fact, completely shocking, was how much of it there was compared to water. The final, calculated ratio of carbon dioxide to water vapor in the coma was 8.0, plus or minus 1.0. Let that number sink in. For every single molecule of water, the stuff that is supposed to be the primary ingredient of a comet, this object was venting 8 molecules of carbon dioxide. In plain English, this comet is made of the wrong stuff. Remember the classic analogy. Comets are dirty snowballs. That is a phrase every schoolchild learns. The snow in that analogy is, and has always been, water ice. Other volatile substances like carbon monoxide, carbon dioxide, methane, and ammonia are supposed to be the dirt, the trace components, the secondary ices mixed in with the dominant water. Finding a comet where carbon dioxide is the main event, the star of the show, is like finding a snowman made almost entirely of dry ice. It is physically possible, but it is so far outside of our normal experience that it forces us to ask fundamental questions. Let me give you the numbers for context so you can appreciate the scale of this anomaly. In the vast majority of comets we have studied, the CO2 to H2O ratio is well below 1. A ratio of 0.1, meaning 10 times more water than carbon dioxide, is common and typical. A ratio of 0.5, or half as much CO2 as water, would be considered on the high side. A ratio of 2 or 3 would be highly unusual and would spark its own scientific papers. A ratio of 8 is basically off the charts. And this wasn't a fluke. As we mentioned, the Spheric Space Telescope backed up this finding, detecting that enormous CO2 coma nearly the size of the Earth-Moon system, without seeing comparable amounts of water. The carbon dioxide dominance is a real, consistent, and deeply bizarre feature of this object. So, how do we explain this? Let's be good scientists and start with the natural hypotheses, because that is always where the search for answers must begin. Hypothesis 1. Formation location. Comets are leftovers from the birth of stars and planets. They form in the frigid outer regions of protoplanetary disks, where temperatures are cold enough for volatile gases to condense directly into ice. But different molecules freeze at different temperatures, creating snow lines in the disk. Water ice, for example, condenses at a relatively warm 150 to 200 Kelvin, about minus 123 to minus 73 degrees Celsius. Carbon dioxide, however, needs much colder conditions to freeze, around 60 to 80 Kelvin, about minus 213 to minus 193 degrees Celsius. It is therefore plausible that 3I Atlas formed in a particularly cold, distant region of its birth system, far out beyond the carbon dioxide snowline. In such a location, it might have naturally accumulated far more CO2 ice than water ice. This is a very sound and scientifically plausible explanation. Hypothesis 2. Radiation processing. Interstellar space is not truly empty. It is filled with a constant shower of high-energy cosmic rays and ultraviolet starlight. Over the millions of years that 3I Atlas wandered between the stars, this relentless radiation could have chemically altered its surface, creating a kind of radiation crust. This process might have broken apart the water molecules on the surface or driven them deeper into the nucleus, leaving behind a surface layer that was depleted in water, but still rich in the more robust carbon dioxide. If this were the case, what we are seeing now is the sublimation of this ancient processed crust. This hypothesis makes a clear, testable prediction. As the comet gets closer to the sun and this crust erodes away, fresher, water-rich ice from the interior should be exposed. If that happens, the CO2 to H2O ratio should decrease over time, eventually flipping to a more normal water-dominant state. Hypothesis 3. Grain-driven release. Sometimes, water ice in comets isn't free and exposed on the surface. It can be trapped inside the structure of dust grains or locked away in cage-like ice formations called clathrates. If the water in 3I Atlas is sequestered in this way, it would sublimate much more slowly than the freely available carbon dioxide ice on the surface. So, early in the comet's approach to the sun, you would naturally see a lot of CO2 and not much H2O later. As the temperatures rise and the dust grains begin to break down and release their trapped water, the water release would catch up. Again, this hypothesis predicts a changing ratio. If the extreme 8-to-1 ratio persists, even as the comet gets hotter and passes the sun, that becomes very difficult to explain with these grain-driven models. All three of these natural hypotheses are scientifically sound. They are consistent with known physics and chemistry. They do not require us to invoke anything exotic or alien. But they do require 3I Atlas to be a very specific and somewhat rare type of object, one that either formed in a very particular place or underwent a very particular history of radiation exposure. Now, let's look at the data through that other lens. Let's engage in that what-if thought experiment. If 3I Atlas were artificial, if it were a spacecraft or a probe, would its chemistry make any sense? As we've touched upon, from an engineering standpoint, carbon dioxide makes a fantastic working fluid. In the harsh vacuum of space, a spacecraft generates a lot of waste heat from its power systems and electronics. You cannot get rid of this heat through conduction or convection, as there is no air to carry it away. You must either radiate it away passively with large radiator panels, which is slow, or you can actively vent the fluid that carries the heat away with it in a process called evaporative cooling. Carbon dioxide is an almost perfect choice for this. It is stable, non-corrosive, sublimates at manageable temperatures, and has excellent thermodynamic properties for heat transfer. In fact, advanced CO2-based refrigeration and cooling systems are already used in high-tech applications right here on Earth. Imagine a probe that uses the sun as intense heat to power its onboard systems, perhaps through advanced solar panels or some kind of thermal-to-electric generator. Those systems would inevitably generate waste heat. Venting carbon dioxide gas would be a simple, elegant, and passive way to shed that heat and maintain a stable internal temperature. And the closer the probe got to the sun, the more power it would generate, the more waste heat it would produce, and the more CO2 it would need to vent. Water, by contrast, is an engineer's nightmare for a system like this. It freezes at inconveniently high temperatures. Its expansion upon freezing can break pipes, and it can be highly corrosive over long periods. If you were designing a thermal management system for a long-duration interstellar spacecraft, you would probably avoid using water as your primary coolant. So, from a purely engineering perspective, the 8-to-1 ratio isn't just plausible for an artificial object. It is precisely what you might expect. And this is the huge critical, but it is also what you might expect from a natural comet with a very specific and unusual formation history. The chemistry alone, as bizarre as it is, cannot definitively distinguish between the two hypotheses. It leaves us in a state of perfect, tantalizing ambiguity. What would help us distinguish them? What is the key that could unlock this mystery? It is time evolution. If 3I Atlas is natural, its volatile composition should change as it heats up and cools down. As it passes perihelion and the surface layers are stripped away, the deeper, more primordial ices should be exposed. We should see the water content start to rise. The 8-to-1 ratio should drop to 4-to-1, then 2-to-1, and perhaps flip entirely so that water is dominant on its way out of the solar system. But if it is artificial and the CO2 is being vented to regulate a system, the ratio might stay roughly constant. The rate of venting would be determined by the engineering requirements of the spacecraft's power systems, not by the simple thermodynamic sublimation of natural ice. The prediction is therefore crystal clear. We must watch the carbon dioxide to water ratio like a hawk, both during its approach and, crucially, after it re-emerges from behind the sun. If the ratio changes in predictable ways, the natural comet hypothesis wins. If it does not, if it remains stubbornly fixed at 8-to-1, then the natural hypothesis is in serious trouble. This is a place where citizen science can play a real role. Amateur astronomers with sophisticated backyard telescopes and specialized filters can track the chemical composition of the coma over time, providing a level of continuous, round-the-clock coverage that professional observatories, with their overbooked schedules, often cannot match. But let's zoom out from the chemistry for a moment. This single, profound chemical anomaly is only one piece of a much larger and more complex puzzle. The other piece, as we began with, is the trajectory itself. And when you look not just at where 3I Atlas has come from, but where it is going, the remarkable sequence of planetary encounters it is about to thread, you start to see something that looks less like a random walk and more like a game of orbital chess. And whether it is nature as game or someone else, as is the question that should keep us all watching the sky. There is a concept in the world of space exploration so elegant and powerful that it feels like magic. It's called a gravity assist, or a slingshot maneuver. You have seen it in action, even if you didn't know its name. It is the secret sauce that allowed our Voyager spacecraft to tour the outer solar system, and it's how the New Horizons probe found the energy to make its historic flyby of Pluto. In essence, it is a technique where a tiny, fragile spacecraft steals a minuscule amount of orbital energy from a colossal planet. By arriving at exactly the right place, at exactly the right time, and at exactly the right velocity, the spacecraft can use the planet's immense gravity to bend its trajectory and slingshot it away at a much higher speed, all without burning a single drop of precious fuel. It is a game of cosmic billiards, a form of orbital chess where every move must be planned with pinpoint precision years in advance. Now, to be perfectly clear, 3I Atlas is not performing a gravity assist in this formal engineering sense. It is not being captured by planets or using them to gain velocity. But its path through our solar system, this flight plan we've discussed, does thread a sequence of close planetary approaches that, if you were a mission planner designing a reconnaissance tour, would be considered textbook. It is a journey that seems to hit all the highlights, a choreographed dance through the most interesting neighborhoods of our solar system. So, what does this grand tour look like? Let's walk through the itinerary, stop by stop. First waypoint, the Red Planet. On October 3rd, 2025, just days from now, and just before it enters its Great Disappearing Act, 3. I-Atlas will pass within approximately 30 million kilometers of Mars. In human terms, that is an enormous distance. But in the vastness of space, it is close enough to be incredibly interesting. It is not close enough for Mars' gravity to have any meaningful effect on the object's path, but it is a golden opportunity for observation from a completely different perspective. The European Space Agency has already confirmed that it will be a diligent host for this encounter. They plan to redirect their 2 active orbiters at Mars, the veteran Mars Express and the state-of-the-art Trace Gas Orbiter, to turn their instruments away from the Martian surface and aim them at this fleeting interstellar ghost. Why does this matter so much? Because Mars offers us a second set of eyes, a different vantage point in the cosmic theater. This creates a baseline for triangulation. Imagine trying to judge the shape and distance of an object with only one eye open. It's difficult. With 2 eyes, you get depth perception, a 3-dimensional view. By observing 3-eye atlas from both Earth and Mars simultaneously, we get that depth. This geometry is particularly favorable for studying the very features that are most anomalous, the sunward coma structure, the very place where Avi Loeb claims to have seen those headlights. An observation from Mars could potentially confirm or refute that claim. Now, the mission planners at the European Space Agency have been careful to temper expectations. Mars Express and the Trace Gas Orbiter are, as their names suggest, optimized to study Mars. They were not designed to be comet-hunting spacecraft. Pointing them at a distant, faint, and fast-moving target is a challenging secondary science objective. The signal will be faint, the data will be noisy, and the resolution won't be great. But even marginal data is infinitely better than no data at all. And if the comet is indeed venting asymmetrically, or showing unusual brightness patterns, the Mars orbiters just might catch it in the act. From a speculative reconnaissance standpoint, of course, Mars is a prime target. As a world with a dynamic atmosphere, weather, and a complex geological history, it is a place you would absolutely want to survey if you are exploring the habitability of a new star system. Second waypoint, the heart of the system. In late October, 3-eye Atlas reaches its fiery climax, perihelion, its closest approach to the Sun. This is the moment of maximum solar heating. For a natural comet, this is when the outgassing and activity should reach a spectacular peak. For an artificial object using the Sun's energy, this is the moment of maximum power availability. And as we know, this is also the moment that the solar conjunction begins the blackout, the gap in our observations. The timing is, from a tactical perspective, perfect. Peak activity coincides with minimum observability from Earth. Third waypoint, the king of the planets. After it survives its trial by fire and re-emerges from behind the Sun, its tour is far from over. On March 16, 2026, 3-eye Atlas is scheduled to make a pass within 0.358 astronomical units, a staggering 33 million miles of the planet Jupiter. To put that in perspective, Jupiter's own volcanic moon Io orbits at a slightly closer distance. A comet will not dive deep into the Jovian system, but it will get close enough for some truly spectacular science. And this is where things get really interesting, because Jupiter isn't just the largest planet in our solar system. It is a magnetospheric powerhouse. It is a world of unimaginable scale and violence, generating the most powerful planetary magnetic field in the solar system. A field that extends for millions of miles into space, an invisible bubble of influence that is hundreds of times larger than the Sun itself. This magnetosphere is a seething cauldron of charged particles, plasma, and intense radiation belts. When any object passes through this environment, it interacts with it. Dust grains get electrically charged. Plasma tails, different from the normal dust and gas tails, can form. If an object has any conductive properties, if it is made of metal, or if it is venting ionized gas, Jupiter's magnetic field will affect it in predictable ways. From a scientific standpoint, this Jupiter flyby is a golden opportunity. By this point, we will have a long arc of observational data. If the Juno spacecraft is still operational and can observe the comet up close, if the James Webb Space Telescope can be aimed at it, and if our ground-based telescopes on Earth are watching, we will have multiple vantage points separated by hundreds of millions of kilometers. This is stereoscopic observation on a solar system scale. It would allow us to reconstruct the three-dimensional structure of the coma, to measure how its composition changes at different distances from the nucleus, and to watch, in real time, how it interacts with Jupiter's colossal magnetic field. And from that speculative reconnaissance standpoint, Jupiter is the crown jewel of any planetary flyby tour. If you are a probe surveying our solar system, you absolutely must gather data on Jupiter, its fascinating ocean-bearing moons, its complex magnetosphere, and its turbulent atmospheric dynamics. Jupiter is a physics laboratory and a miniature solar system all in one. So the sequence is clear: Mars, Sun, Jupiter. 3 distinct environments. 3 unique opportunities for observation. Or, if you are entertaining the artificial hypothesis, 3 prime targets for data collection. Now, we must perform our reality check. This is where we ground ourselves again in the science we know to be true. As we stated, this is not a gravity assist tour in the mission design sense. The object passes of Mars and Jupiter are too distant for their gravity to radically change its course. The object is following a heliocentric orbit, a path determined almost entirely by its initial incredible velocity and the relentless pull of the Sun's gravity. The planetary encounters are, under the natural hypothesis, simply incidental, geometric coincidences based on where the planets just happen to be in their own orbits when the comet passes through. But here is the nuance, the very heart of the mystery. If you were planning a survey mission, you wouldn't necessarily need gravity assists. You would just need a trajectory that provided you with close, information-rich flybys of your most interesting targets. And the trajectory of 3I Atlas does exactly that. The public predictions of its path, published by NASA's Jet Propulsion Laboratory, are currently consistent with purely gravitational motion. As far as our measurements can tell so far, the object is following a simple ballistic path governed by gravity alone. But all of those crucial measurements were taken before the solar conjunction. If something changes during the blackout, if there is a subtle course correction, a delta V burn, a deployment event, we will not know about it until after it re-emerges. And if that happens, its future path will have diverged from the purely gravitational predictions. So, what patterns should we look for after the conjunction to test whether there is any design, any intent to this trajectory? We should look for changes in its phase curve, the way its brightness changes as our viewing angle shifts, which could indicate a change in its surface properties. We should look for timing residuals, evidence that it is arriving at predicted points in space slightly earlier or later than expected, which would be a smoking gun for acceleration. We should look for orientation changes, a shift in its rotation that could hint at internal mass redistribution or external forces. We can do all of these things with our existing telescopes. It is just a matter of time, coordination, and careful analysis. If 3I Atlas is following a designed itinerary, then the Mars and Jupiter encounters are waypoints, checkpoints on a tour. But if it is natural, then they are just random dots on a cosmic map. How do we tell the difference? We watch, we measure, we test the predictions against the cold, hard reality of observation. If the object behaves exactly as gravity and natural solar heating predict, then coincidence wins. But if there are deviations, however small, then the design hypothesis gains a traction it has never had before. And speaking of design, there is one audacious proposal that has been circulating, moving from the pages of peer-reviewed journals all the way to the halls of Congress. It is a proposal that could settle many of these questions, not with passive observation, but with an active, daring, and incredibly risky mission, a spacecraft intercept. And the spacecraft in question is already out there, waiting. Its name is Juno. For weeks, we have been observers. We have been cosmic detectives, piecing together clues from a distance of hundreds of millions of miles, trying to build a case from faint photons of light that have traveled across the void. We have debated trajectories, analyzed chemical fingerprints, and scored anomalies on a scale of strangeness. But what if we could do more? What if we could stop being passive observers and become active explorers? What if we could send a messenger of our own to meet this mysterious traveler, to look it in the eye and uncover its secrets up close? It sounds like the stuff of a Hollywood blockbuster, a mission that would take decades to plan and launch. But what if I told you that a credible plan exists to do it right now? A plan that is audacious, incredibly risky, and just barely possible. On September 20th, 2025, a peer-reviewed paper appeared in the scientific journal Aerospace. It was not a paper filled with speculation or theory, but with the hard, cold, beautiful mathematics of orbital mechanics. Its title was provocative and direct, using NASA's Juno spacecraft to intercept 3I Atlas. This was not science fiction. This was a flight plan. The star of this plan is Juno, one of NASA's most successful and beloved flagship missions. Since July 4, 2016, Juno has been in a looping elliptical orbit around the colossal planet Jupiter, studying its powerful magnetic field, its deep, turbulent atmosphere, and its mysterious interior structure. It has painted a new and stunning portrait of the king of the planets. As of 2025, the mission is still operational, still returning incredible data, and still a jewel in the crown of planetary science. But Juno has a secret weapon. Tucked away in its structure is a main engine, a powerful thruster that has been dormant for 9 long years, ever since it was fired to put the spacecraft into orbit around Jupiter back in 2016. For nearly a decade, it has been silent, cold, and unused. But theoretically, it still works. And theoretically, it still has propellant left in its tanks. This dormant engine is the key to one of the most daring gambits in the history of space exploration. The proposal, laid out in meticulous detail by trajectory dynamics researchers, hinges on a powerful technique called an Oberth maneuver. The physics behind it is both simple and profound. When you are deep inside a powerful gravity, well, like Jupiter's, you are moving at an incredible speed. The Oberth effect states that firing your engine at this moment of maximum velocity produces a disproportionately huge change in your final trajectory. You are, in essence, using the planet's own immense potential energy to amplify the thrust of your engine. It is the ultimate cosmic slingshot. Here is the proposed timeline for this audacious plan. On September 9th, 2025, Juno would perform one of its close passes over Jupiter's swirling cloud tops, a moment called a perijove. And at that exact moment of closest approach and highest speed, Mission Control on Earth would send a command that has not been sent in 9 years. Fire the main engine. The burn would be significant, requiring a change in velocity, delta V of approximately 2.68 kilometers per second. To put that in perspective, that is more thrust than the descent engine of the Apollo lunar module used to land astronauts on the moon. This would be a real, mission-class engine burn, a violent, transformative event that would shatter Juno's stable orbit. That single, powerful push would send Juno onto a hyperbolic escape trajectory, flinging it away from Jupiter and back toward the inner solar system on a precision-guided intercept course. Then, after a 6-month chase across hundreds of millions of miles, On March 14, 2026, Juno would intercept 3I Atlas. The encounter would be a high-speed flyby, with a relative velocity of around 19 kilometers per second, far too fast to enter orbit, but perfect for a close-up reconnaissance pass. At its closest approach, Juno would streak within just a few thousand kilometers of the object's nucleus. And at that moment, it would unleash its entire suite of powerful scientific instruments. What instruments does Juno have that would be so useful? It just so happens to be almost perfectly equipped for this very mystery. Its infrared spectrometers, GIRM and GIMS, designed to study Jupiter's auroras, could measure the temperature of the nucleus and precisely map the composition of the corona, settling the carbon dioxide and nickel mysteries once and for all. Its ultraviolet spectrograph, UVS, would map the distribution of key gases, giving us a 3D picture of the outgassing. Its magnetometer, MAG, could detect how the object interacts with the solar wind, and critically, could reveal whether the object itself possesses any anomalous magnetic properties, a key signature of technology. Its WAVES instrument, which listens for radio and plasma waves, could detect any electromagnetic activity, any emissions, natural or otherwise, coming from the object. And then there is JunoCam, officially a public outreach camera, not a primary science instrument. JunoCam has nonetheless taken some of the most stunning, high-resolution images of Jupiter we have ever seen. At a range of a few thousand kilometers, JunoCam could provide us with the first ever close-up, detailed photograph of the nucleus of an interstellar object. It would resolve the headlights debate. It could show us if the object is a rubble pile or something more structured. It would give us the money shot. So Juno is the right tool for the job. The problem isn't the instruments. The problem is the risk. That main engine has not fired in 9 years. In the harsh environment of space, things break. Propellant can settle in its tanks. Valves can stick. Seals can degrade. There is a very real, non-zero chance that when you send the command to fire, the engine simply doesn't ignite. Or worse, it fires partially or erratically, sending the multi-billion-dollar spacecraft into an uncontrolled and unrecoverable tumble. If the burn fails, Juno would be lost. You would be throwing away a flagship mission that is still producing world-class, Nobel Prize-worthy science at Jupiter, all for a single high-stakes roll of the dice. The authors of the paper noted that they had contacted the Juno mission team at NASA. The response, as reported in the paper, was understandably cautious. The team acknowledged that propellant reserves likely exist, but that undertaking such a major, mission-altering burn would require a formal, top-to-bottom review, a rigorous risk assessment, and crucially, approval from the highest levels of NASA headquarters. There is, as of now, no official plan to do this. But this is where the story gets political. In late 2025, after the paper was published, Representative Anna Paulina Luna, a member of the U.S. Congress, sent a formal letter to the administrator of NASA, urging the agency to seriously study the feasibility of using Juno for a 3I Atlas intercept. The letter emphasized the unprecedented scientific value of getting in situ measurements of an interstellar object and highlighted the unique, fleeting opportunity presented by the timing and geometry. Nudges like this from Congress matter. They don't guarantee action, but they signal high-level political interest, which can unlock funding, shift priorities, and force an agency to give an idea serious consideration. If Congress is paying attention, NASA has to, at the very least, respond. This is NASA's dilemma. It is a choice that would make any administrator tremble. Do you protect your working, multi-billion-dollar asset that is guaranteed to produce great science at Jupiter for years to come? Or do you gamble that asset on a risky, one-shot intercept of an object that might, in the end, just be a weird comet? It is a battle between guaranteed success and a chance at immortality. The scientific upside, if it worked, would be almost immeasurable. We have never sent a spacecraft to an interstellar object. An intercept would give us direct, unambiguous measurements of its size, shape, and composition. It would map its magnetic and plasma environment. It would detect any emissions. And it would provide imagery that could settle the debate once and for all. If 3I Atlas is artificial, a Juno flyby would almost certainly reveal it. You would see the structure. You would detect the anomalies. You would get the data that could not be explained away. And even if it turns out to be a completely natural, if weird, comet, the flyby would still be transformative, teaching us about the building blocks of other star systems. So what should we watch for to know if this incredible Gambit is actually being considered? We should watch for official mission updates from NASA. Spacecraft retargeting of this magnitude requires months of intense planning, so any movement would need to start soon. We should watch for any new updated information from the Juno team about their propellant reserves and the health of their main engine. The Juno intercept proposal is a perfect case study in how science, politics, and risk intersect. It is a reminder that we, as a species, now possess the capability to do truly extraordinary things, to reach out and touch the messengers from other stars. The question is, will we choose to? For now, Juno continues its majestic looping dance around Jupiter. 3I Atlas continues its silent inbound trajectory, and the clock continues its relentless tick down towards the solar conjunction, that great, dark window where our vision will fail us. And what happens in that unseen moment could change everything. And so, we stand at the precipice. We have traveled from the mountaintops of Hawaii to the golden mirrors of the James Webb Space Telescope, from the red plains of Mars to the colossal storms of Jupiter. We have followed a trail of baffling clues, a ghostly trajectory, a bizarre chemical fingerprint, a series of cosmic coincidences so profound they challenge our understanding of randomness itself. We have weighed the evidence on a scale of strangeness, debated the forensics of a potential cosmic crime scene, and even dared to dream of an audacious chase mission to intercept the stranger. And now, all the theories, all the data, and all the speculation must fall silent. For we are entering the final, suspenseful act of this drama, the long vigil. The solar eclipse of our awareness is upon us. As we've detailed, in late October 2025, 3I Atlas will slip behind the sun, and for 4 long weeks, it will be gone. Our most powerful telescopes will be rendered blind, our planet's sharpest eyes sealed shut by the glare of our own star. During this period, the object will face its greatest trial, a baptism by fire as it makes its closest approach to the sun. It will be baked, stressed, and blasted by the full raw power of a star. And what happens in that crucible, in that unseen furnace, could change everything. Let's game out the possibilities one last time, the scenarios that await us when the lights come back on in late November. Scenario 1. The sigh of relief. The object re-emerges from the sun's glare, exactly where we expect it to be, its trajectory unaltered. Its brightness has evolved, just as our models of a natural comet predict. New spectra show that the water content is rising, and that bizarre 8-to-1 ratio is starting to normalize. The long-awaited iron emission lines finally appear alongside the nickel, consistent with the heating of natural metal-bearing dust. In this scenario, the blackout was uneventful. The silence held no secrets. 3I Atlas, for all its wonderful strangeness, takes its place in our textbooks as an exceptionally weird, but ultimately natural, comet. Coincidence, however improbable, remains the best explanation. And scientists around the world will breathe a collective sigh of relief, or perhaps a tiny sigh of disappointment. Scenario 2. The lingering ambiguity. The object reappears, but something is slightly off. There are subtle residuals in its position, a tiny deviation from a purely gravitational path that is right on the edge of our measurement error. Astronomers will argue for decades over whether it was evidence of a small, stealthy maneuver or just a particularly strong and unpredictable outgassing event. The chemical ratios remain strange. The data is inconclusive. The mystery endures, passing from a scientific problem into a legend, a cosmic ghost story to be told by future generations of astronomers. Scenario 3. The smoking gun. The object reemerges, and the evidence is immediate and undeniable. Its position is significantly different from the predicted path. The forensics clearly show that a non-gravitational force acted upon it during the blackout. Perhaps sharp-eyed observers spot faint companion objects trailing the nucleus, objects that were not there before. Or perhaps, in the most dramatic of all outcomes, a signal is detected not by us, but by a spacecraft elsewhere in the solar system, a second-hand report of an event we were not privileged to witness ourselves. In this scenario, the score on the Loeb scale jumps to a 7, an 8, or even higher. The world would be changed forever. The conversation would shift from the halls of science to the halls of government. We would know, with a chilling certainty, that we are not alone. Each of these scenarios is possible. Some are, of course, far more likely than others. The overwhelming scientific expectation, the default assumption, is scenario 1. But the fact that scenarios 2 and 3 are even plausible is what makes this moment in history so electrifying. Even during the blackout, we will not be completely without eyes. As we've discussed, the European Space Agency's orbiters at Mars may have caught a fleeting glimpse before the main event. Classified sensors, the hidden eyes of military and intelligence agencies, might detect an anomalous thermal event. And there is always the slim possibility that the James Webb Space Telescope, through a lucky quirk of geometry, might be able to steal a precious observation. But the flow of this information to the public could be delayed by weeks, months, or in the case of classified data, indefinitely. We must remember that in the end, the decision to reveal a world-changing discovery is a human one. So what does this all mean for us right now, as we stand on the cusp of this great unknown? The story of 3I Atlas was never just about a comet. It has become a mirror. It is forcing us to confront some of the most profound questions we can ask. It is a story about how we, as a species, deal with profound uncertainty. Are we willing to entertain extraordinary possibilities while still maintaining the highest standards of scientific rigor? Or do we retreat into the comfort of dogmatic skepticism or the fantasy of wishful thinking? This event is a real-time test of our scientific maturity. It is a call to be both open-minded and hard-headed, to follow the data wherever it leads, even if it leads us to uncomfortable and paradigm-shattering conclusions. It is a reminder that the universe is under no obligation to conform to our expectations. So, I encourage you to watch the skies. In the coming weeks, as 3I Atlas makes its final visible approach, and then in late November, as astronomers around the world scramble to reacquire it, pay attention. Read the reports from amateur and professional observers. Look for the data on its position, its brightness, its chemistry. Watch the score on the Loeb scale evolve. You are living through a unique moment in history, a genuine scientific mystery unfolding in real time. Regardless of the outcome, whether it is a rock or a relic, the journey of 3I Atlas has already given us a gift. It has reawakened our sense of wonder. It has reminded us that we live in a universe that is still largely unexplored, filled with secrets and possibilities beyond our wildest imaginings. It has forced us to look up from our daily lives and contemplate our place in the vast, silent and possibly very crowded cosmos. The silence before the sun is almost here. The countdown has begun, and when the lights come back on, we will see what's really out there. Thank you for joining me on this journey into the heart of the mystery. I hope you learned something new, and I hope you feel, as I do, a renewed sense of awe for the grand, unfolding story of the cosmos. Whatever comes next, we will face it with curiosity, with rigor, and with our eyes wide open. Good night.